What if the red planet just answered back? Within hours of interstellar object 3I Atlas sweeping past Mars, NASA's MAVEN spacecraft recorded a sudden magnetic surge, like a cosmic heartbeat rippling through the Martian sky. At the same time, a burst of plasma raced across the solar wind, bending field lines in ways no model had predicted. The timing was too perfect to ignore, a silent visitor from beyond the stars and a shockwave no one saw coming. Scientists are now dissecting the magnetometer data, searching for an origin that fits known physics, but the numbers don't add up. Could something about 3I Atlas have interacted with Mars' fragile magnetic field or triggered something deeper within it? Stay with me because by the end of this investigation, you might begin to question what really defines natural in the vacuum between worlds. Shock of coincidence. What are the odds that two cosmic events, each rare on its own, would unfold within hours of each other, right above the rusted deserts of Mars? On one side of the solar system, interstellar object 3I Atlas carved its path through the void, a glowing green visitor moving faster than any comet born within our sun's domain. On the other, NASA's MAVEN spacecraft began recording a strange and violent shift in magnetic energy. The readings spiked so abruptly that for several minutes the magnetometer data resembled the pulse of a storm. Yet there was no storm. No coronal mass ejection, no solar flare, nothing from the sun that could explain it. At first, scientists thought it was a calibration error, but the timestamps didn't lie. The surge began less than 3 hours after 3 Atlas's closest flyby with Mars, too soon, too specific, and too intense to ignore. MAVEN sensors showed an increase in plasma density, a twisting of the magnetic field lines, and a transient wave pattern moving across the upper atmosphere. To most researchers, it was an anomaly. To a few, it looked like something else entirely, an induced disturbance, as though an external magnetic source had passed nearby and dragged the Martian field with it. Mars is not like Earth. It has no global magnetic field to protect it from the chaos of space weather. What it has are scattered remnants, patches of magnetized crust buried beneath the surface, faint echoes of an ancient dynamo that died billions of years ago. These localized fields interact with the solar wind, creating flickering auroras and thin plasma currents that dance above the planet's poles. They are fragile, reactive, and easily perturbed, which makes the MAVEN data even more haunting. Because on the night 3I Atlas passed, those faint Martian magnetic scars seemed to come alive. The magnetometer readings climbed, dipped, and oscillated in rhythmic pulses. Plasma wave instruments detected bursts of charged particles rising from the ionosphere. Even the spacecraft's accelerometers registered tiny variations, as if the atmosphere itself had been brushed by an unseen hand. NASA's mission logs mark the event simply as a localized magnetic anomaly. But among those who've studied MAVEN's archives for years, that phrase means something much stranger: an energetic disturbance without a known cause. Back on Earth, astronomers continued to track 3I Atlas as it moved toward the inner solar system. They noted the brightness variations, the fragmented coma, the faint tail that seemed to defy normal physics, pointing both toward and away from the sun, forming an antitail that glowed with cyan light. It was already a mystery, wrapped in plasma and speculation. But now, there was a new question to add to its growing legend. Had it just rattled the magnetic skeleton of an entire planet? Some researchers suggested that what MAVEN detected could have been a delayed echo of a distant solar event, a blast wave from a coronal ejection that hit Mars earlier than predicted. But solar observatories recorded nothing of the sort. No major flare, no incoming storm, no solar particle burst. The heliospheric models didn't align with the timestamps. The solar wind speed at Mars's orbit that night was normal, its density unremarkable. So, if not the sun, what else could have caused the surge? The data hinted at a magnetic compression wave, a sudden tightening and relaxation of the local magnetic environment. These can occur when a fast-moving object carrying an embedded magnetic field enters a plasma-rich region. If 3I Atlas carried even a weak field, perhaps generated by a conductive core or remnants of ionized material, it could have briefly merged with Mars-induced magnetosphere. For a few minutes, the two fields might have interacted, releasing energy as they untangled. It's only a hypothesis, one that remains highly speculative, but it would explain the shape of the MAVEN signatures almost perfectly. What makes the timing even more unsettling is how precise it was. The magnetic surge began 167 minutes after 3I Atlas reached periapsis near Mars' orbit. That's within the travel time for plasma shockwaves to propagate through the solar wind at typical velocities. In other words, the delay wasn't random, it fit a physical time frame. Coincidence? Possibly. But even seasoned planetary scientists admit that coincidences like this tend to raise eyebrows, especially when data align across multiple instruments. In the following hours, MAVEN detected smaller secondary fluctuations like aftershocks, each one diminished in amplitude, fading over the next Martian day. The team cross-referenced the anomalies with orbit data, checking for spacecraft interference or electrical noise. None matched. Whatever happened occurred externally, something in the Martian environment itself. MAVEN's solar wind analyzer confirmed that ambient plasma temperature had spiked by 18%, then abruptly dropped. Even the spacecraft's ultraviolet sensors saw a brief increase in atmospheric glow, concentrated near the southern hemisphere where crustal magnetic fields are strongest. From orbit, the event might have looked like a silent aurora. No visible storm, just faint waves of light rippling across thin air. A planet with no magnetic heart suddenly convulsing as if something invisible brushed against it. The poetic might call it a whisper from the cosmos. The skeptical would call it noise. But the data remain. Meanwhile, Earth-based telescopes captured faint green emissions from 3I Atlas's coma. Strange, because the spectral lines didn't match typical cyanide or diatomic carbon emissions. Something else, perhaps exotic ionized metals or magnetically aligned dust, was scattering the sunlight. Some plasma physicists noted that if such particles were charged enough, they could create localized electromagnetic disturbances in nearby environments, especially within the weak magnetospheres of smaller worlds. Mars, with its patchwork field and thin atmosphere, would be particularly susceptible. The idea that an interstellar object could affect a planet magnetically seems wild, but so did the discovery of Oumuamua's non-gravitational acceleration back in 2017. The cosmos has a habit of breaking its own rules. Every time astronomers think they've mapped the boundaries of physics, something from beyond the solar system drifts in and rewrites them. Still, not everyone is convinced. Many in the scientific community warn against overinterpreting data. A one-time magnetic spike could just as easily be an instrumental artifact, an echo of MAVEN's own electronics, or a rare solar microburst unseen from Earth. The problem is, MAVEN wasn't the only observer. The European Space Agency's Trace Gas Orbiter also recorded minor fluctuations in ion density around the same time frame, though its instruments weren't as sensitive. 2 spacecraft, 2 independent readings, 1 event. That's harder to dismiss. Even more intriguing, the magnetic orientation of the surge matched the predicted vector of 3 Atlas's trajectory, angled approximately 32 degrees relative to the ecliptic. In other words, the disturbance came from the same direction as the visitor. The statistical likelihood of that alignment being random? Less than 1 in 50, according to one analyst. The pattern is small, subtle, and could still be coincidence, but it's enough to make some researchers quietly wonder if Mars just experienced the first documented magnetic interaction with an interstellar object. If that's true, the implications are staggering. And it would mean 3I Atlas isn't just a rock or icy nucleus. It might be carrying something active, either a residual magnetic field or an electrically charged plasma sheath generated during its long interstellar journey. Some theorists even suggest such objects could act as magnetic seeds, influencing the environments they pass through, leaving invisible signatures behind. It's a bold idea, one bordering on science fiction, but so was the notion of objects from beyond our solar system until only a few years ago. For now, NASA has neither confirmed nor denied any connection. MAVEN's data has been archived and the event labeled under review. But within the research community, whispers persist. Some call it the Mars Shockwave, others, more dramatically, the cosmic pulse. And somewhere in that thin Martian sky, above dust storms and silent valleys, the remnants of that invisible wave may still be echoing. A pulse that began when a visitor from another star passed too close, and Mars, for just a moment, seemed to react. Flyby profile. It began as a faint smear of green light beyond the orbit of Jupiter, an unassuming blur that defied every initial prediction. When astronomers first calculated the trajectory of 3I Atlas, they realized it wasn't bound to the Sun. Its hyperbolic path confirmed it as only the third known interstellar object ever detected, following Oumuamua and Borisov. But unlike its predecessors, this one wasn't passing quietly. 3I Atlas was already emitting. Even in the cold darkness where comets usually sleep, it shimmered faintly, as though carrying its own internal energy. As it neared the inner solar system, its projected course brought it dangerously close to the orbit of Mars, an encounter no planetary scientist expected. Most interstellar visitors pass through undetected, barely influencing the worlds they sweep by. But 3I Atlas was different. From the moment it entered the heliosphere, it began to misbehave. Telescopic arrays tracking its inbound velocity recorded subtle irregularities, tiny deviations in speed and vector, unaccounted for by gravity alone. Some attributed this to outgassing jets, but even those didn't fit the observed thermal models. The object wasn't rotating or venting like a comet. Instead, its trajectory showed smooth, consistent acceleration, as if guided by a uniform external force. The effect was subtle but measurable, a few millimeters per second per day, enough to raise eyebrows among mission analysts. By the time it crossed Mars's orbital plane, 3I Atlas had already become one of the most scrutinized bodies in space. NASA, ESA, and even private observatories tuned their instruments toward it. MAVEN, already orbiting Mars to study atmospheric loss, was tasked with recording any magnetic or plasma activity during the flyby window. No one expected anything dramatic until the numbers arrived. 3I Atlas passed within 0.02 astronomical units of Mars, about 3 million kilometers. That might seem distant, but in interplanetary terms, it's close enough for magnetic interactions if the object carried a charged sheath. The geometry was perfect for it. Mars on the downstream side of the solar wind, 3I Atlas passing nearly perpendicular to the Sun's field lines. For just a few hours, their plasma environments overlapped in a way that simulations rarely capture. During that time, MAVEN's magnetometer began to flicker. A faint ripple, at first indistinguishable from background noise, slowly amplified. The spacecraft's plasma analyzer recorded an unexpected shift in ion composition. Higher concentrations of O-pi and CO2-pi ions, the very species that dominate Mars's upper atmosphere. Something was stirring the ionosphere. Ground-based observatories in Chile and Japan noted simultaneous brightness fluctuations from 3I Atlas. Its coma brightened by nearly 30%. Before dimming again. Some called it outgassing, but the light curve lacked the chaotic spikes typical of volatile release. Instead, it was smooth, like an electromagnetic surge radiating through the surrounding plasma. When MAVEN's orbit carried it through Mars' nightside terminator, the spacecraft sensors recorded the sharpest deviation yet, a clean magnetic pulse rising from 25 to 48 nanotesla in under a minute. That's not the Sun, that's local. Whatever brushed past Mars, it did so with invisible force, tugging on the planet's induced magnetosphere like a current, snapping a wire. To reconstruct the event, scientists plotted the geometry in simulation. At the exact moment of the spike, 3I Atlas was passing along the solar wind's bow shock region relative to Mars. Picture the solar wind like a river of charged particles flowing from the Sun, and Mars as a rock deflecting that current. 3I Atlas moved through that wake zone, potentially altering how the current bent around the planet. If its own plasma sheath or magnetic field intersected the Martian bow shock, it could have compressed the field lines, causing the shockwave MAVEN detected. The question then became, could an interstellar object really carry a magnetic field across light years? Normally, magnetic fields decay rapidly in open space, but theorists argue that if 3I Atlas traveled through dense interstellar plasma, it could have accumulated a layer of ionized dust, a sheath that preserved residual charge. As it entered the heliosphere, the Sun's magnetic field might have re-energized that layer, transforming the object into a moving magnetic anomaly. The physical dimensions of 3I Atlas are still uncertain. Estimates vary from 800 meters to several kilometers long, but spectral modeling suggests it's elongated, possibly spindle-shaped, like a tumbling shard of ice and metal. Observations from the Hubble Space Telescope hinted at a metallic reflectance signature uncommon for comets, closer to nickel-iron alloys than silicates. If true, that composition could allow for electrical conductivity far beyond typical icy bodies. In essence, 3I Atlas might have acted like a vast moving conductor, generating electromagnetic interactions as it sped through the solar wind, and speed was its greatest weapon. Traveling at nearly 95 kilometers per second relative to the Sun, 3I Atlas cut through the heliospheric magnetic field like a knife through fabric. The faster an object moves through plasma, the more intense the induced currents around it become. For a few minutes during its Mars flyby, those induced fields may have overlapped directly with the planet's own, creating interference patterns that MAVEN interpreted as a storm. NASA's official statement, however, remains cautious. In archived mission notes, the phrase correlative anomaly appears next to the timestamp. But internal memos circulated among MAVEN researchers reportedly described the incident as a transient magnetic compression uncorrelated to solar drivers. In simpler terms, it wasn't the Sun. Something else caused it. Even more puzzling were the spectral emissions recorded by Earth-based spectrometers during the same window. 3I Atlas's coma emitted strong cyan-green light associated with ionized nickel and carbon chains, rare even for active comets. Some scientists suspect those emissions could be magnetically excited, meaning the object's own field, or an induced one, was influencing its surrounding plasma. When plotted against MAVEN's data, the correlation was uncanny. The brightening of 3I Atlas and the magnetic surge at Mars occurred within the same 2-hour window, separated by only a propagation delay consistent with solar wind transmission speeds. Two instruments, two worlds apart, recording two expressions of the same invisible wave. This wasn't the first time Mars had experienced magnetic turbulence. During solar maximum, coronal mass ejections can compress its induced magnetosphere dramatically, but those events are always preceded by flares detected days in advance. None were seen that week. The Sun was unusually calm, its X-ray flux flatlined. The odds of such an isolated, well-timed pulse being random grow smaller with every dataset examined. There's another layer to the story, an almost poetic symmetry. As 3I Atlas exited Mars's orbital corridor, the planet was entering its perihelion season when its thin atmosphere becomes electrically charged by solar radiation. MAVEN has documented electric double layers forming in the upper ionosphere during this period, like shimmering veils of trapped energy. If the interstellar visitor's field interacted with those layers even briefly, it could have released stored charge in a sudden burst, a planetary discharge mistaken for a magnetic storm. Imagine Mars, a quiet world with only the faintest heartbeat of magnetism, suddenly resonating like a struck bell as an alien current passes overhead. For a few moments, the two environments, Martian and interstellar, became one. And then, just as quickly, silence. In the days that followed, 3 Atlas continued on its way, glowing brighter than expected as it approached the Sun. Some speculated that the Mars encounter had triggered a reaction, perhaps heating from induced currents or the shedding of charged dust. But without direct sampling, it remains guesswork. MAVEN's team downloaded terabytes of data, cross-checked instruments, and ran plasma simulations until the results blurred into speculation. The only conclusion they could agree on: the timing was too perfect to dismiss. Astrophysicists are now exploring whether interstellar objects might routinely interact with planetary magnetospheres. Every planet leaves an invisible footprint in the solar wind, a plasma trail that stretches millions of kilometers. If a fast-moving, magnetized object crosses one, the results could be detectable as transient magnetic waves or auroral outbursts. In other words, Mars may not be unique. It may simply be the first to witness such an encounter up close. Yet beneath the technical data lies something more unsettling. For centuries, humans have looked to Mars as a mirror, a world that once had rivers, perhaps life, and a magnetic shield like ours. That shield vanished long ago, leaving it exposed to the void. But on the night 3I Atlas passed by, it was as if the universe remembered Mars again, reaching out through magnetic currents to make the planet shiver one more time. The event left behind more questions than answers. Was it a chance alignment, or proof that even interstellar debris carries hidden power? Did 3 Atlas awaken something dormant in Mars's atmosphere, or simply reveal what was already there? Whatever the truth, the MAVEN readings mark a point in cosmic history when two travelers, one ancient and silent, one man-made and vigilant, crossed paths under extraordinary circumstances. The flyby was brief, But for those watching the data unfold in real time, it felt like standing on the edge of discovery. Somewhere between physics and wonder, Mars's magnetic pulse echoed through the numbers, an echo of contact between worlds, and a reminder that even the smallest visitor from the stars can leave an indelible mark on the planets it passes. Mars' fragile shield. Long before humanity sent its first orbiters, Mars once had a magnetic heart. Billions of years ago, molten iron churned within its core, generating a global magnetic field that shielded the planet from the raw violence of the sun. That field sustained an atmosphere thick enough for rivers to flow and oceans to glimmer under a young red sky. But something, perhaps a catastrophic impact, perhaps internal cooling, broke that invisible armor. The dynamo went silent. And with it, Mars began to lose everything that made it alive. Without a protective magnetosphere, the planet became a cosmic target. Solar wind, that relentless stream of charged particles from the sun, slammed into the upper atmosphere day after day, stripping it molecule by molecule. Over eons, what was once a blue, habitable world turned into the frozen desert we see today. The air thinned to less than 1% of Earth's. The oceans vanished, either locked beneath the surface or blown into space. What remained were only ghosts of magnetic fields, ancient imprints preserved in the crust, scattered like buried memories beneath the dust. These magnetic remnants still linger today, concentrated mostly in the planet's southern hemisphere. They form patchy regions where field lines loop and twist unpredictably, each a relic of the planet's lost dynamo. NASA's MAVEN spacecraft has mapped these zones in exquisite detail, revealing clusters of magnetized rock that act like miniature shields. But they're weak, mere whispers compared to Earth's field, and they don't cover the planet uniformly. Mars, in essence, is naked before the sun, and yet it still fights back. When the solar wind collides with the planet's ionosphere, a thin layer of charged gas high above the surface, it induces temporary magnetic fields that wrap around Mars like a translucent cocoon. This induced magnetosphere acts as a reactive defense, reshaping itself with every gust of solar plasma. It's a dynamic system, constantly forming, collapsing, and reforming, and sometimes it resonates, it begins. When MAVEN detected the sudden surge during 3I Atlas's flyby, it was these induced fields that trembled first. The spacecraft's sensors showed a sudden compression of magnetic field lines, followed by oscillations at frequencies consistent with Alphan waves, ripples that travel through magnetized plasma. Normally, such waves are triggered by solar flares or coronal mass ejections, but that week, the sun was quiet. The only visitor in Mars's neighborhood was the interstellar object cutting across its orbital wake. To understand the shockwave, scientists had to revisit Mars's fragile shield from the inside out. At the core of the system lies the bow shock, the invisible frontier where the solar wind slams into the planet's induced field. It's a chaotic boundary, filled with turbulence, electric currents, and charged particles bouncing in every direction. The bow shock acts like a pressure valve, balancing solar energy with Mars' limited resistance. When something disturbs that balance, the entire magnetic structure can ripple outward like a struck drum. During the 3I Atlas event, MAVEN's plasma instruments detected exactly that, a sudden thickening of the bow shock region. The magnetic field strength spiked by nearly 90%, while ion density doubled. For a brief moment, Mars's shield swelled as though bracing for impact, but there was no solar storm to trigger it. No flare, no radiation burst, nothing measurable from the sun. Whatever caused that compression came from local space. The fragile shield analogy is more than poetic, it's literal. Mars's induced field operates like a thin film stretched across chaos. A small fluctuation in the solar wind can send shockwaves racing across its surface. Imagine an invisible curtain fluttering under an electric storm, each ripple amplifying the next. If 3I Atlas carried its own charged envelope, an interstellar plasma sheath, it could have collided with Mars's field like a magnet brushing against a foil balloon. The result: a cascade of distortions moving through the ionosphere recorded by MAVEN as a magnetic storm. What makes this interaction so fascinating is how sensitive Mars is to even the smallest disturbances. On Earth, our magnetic field absorbs and deflects vast amounts of solar energy without noticeable effect. But on Mars, the same pulse could rattle the entire magnetosphere. It's like the difference between striking a gong and striking a tuning fork. The smaller instrument vibrates more easily. Mars is that tuning fork in space, ringing faintly whenever the cosmos brushes by. The MAVEN data captured more than just magnetic spikes. Ultraviolet sensors detected faint auroral emissions, patches of light flickering near the southern hemisphere, directly above one of the planet's crustal magnetic regions. These proton auroras are usually linked to solar events, but no solar activity was recorded. The timing matched the magnetic anomaly almost perfectly. For a few minutes, Mars seemed to glow as if its fractured magnetic shield had momentarily flared back to life. Scientists have long wondered whether these magnetic patches could ever reawaken Mars's lost dynamo. In theory, if enough energy passed through them, they might behave like miniature coils, inducing local currents that release light. That's exactly what MAVEN may have witnessed. The surge of plasma energy, whether from solar interference or the wake of 3I Atlas, appeared to electrify those regions, producing transient auroral bursts. It was as though the ghost of Mars's magnetic field stirred again, alive for a heartbeat before falling silent. When researchers overlaid the auroral data with the object's flyby geometry, something curious appeared. The brightest glow aligned almost perfectly with the point on Mars closest to 3I Atlas's trajectory. That could be coincidence, of course, but coincidences in space have a strange habit of clustering around anomalies. The geometry fit too neatly to ignore. This isn't the first time Mars's induced field has responded mysteriously. In 2017, MAVEN detected magnetic pulses that seemed to travel around the planet like circular waves, even without solar triggers. Some theorists proposed that cosmic rays or charged dust clouds might have caused them. Others hinted at something more complex, plasma resonance modes interacting with Mars' crustal fields. Now, with the arrival of 3 Atlas, that theory gains new fuel. If the interstellar visitor's magnetic sheath intersected with Mars's induced field, it could have created a coupling event, a brief fusion of magnetic lines that transferred energy between them. This would explain the sudden magnetometer spike, the plasma surge, and even the faint auroral emission. It would also mark the first known magnetic interaction between a planet and an interstellar object. But here's the unsettling part. Models of induced magnetospheres show that when such a coupling occurs, it can leave behind residual oscillations, magnetic echoes that persist long after the source is gone. MAVEN's post-flyby data indeed shows faint periodic variations continuing for nearly 40 hours after the main event. Weak but measurable. It's as if Mars continued to hum, resonating long after the visitor had vanished beyond its orbit. Some plasma physicists argue that this afterglow might represent stored energy slowly dissipating from the bow shock. Others think it could be a signature of something larger, a standing wave traveling through the solar wind, possibly originating from 3I Atlas itself. Either way, it reinforces the notion that Mars's shield, fragile as it is, acts like a cosmic amplifier, recording every whisper of electromagnetic change that passes through its domain. The fragility of that shield is both a weakness and a gift. For planetary scientists, Mars is a natural laboratory for studying magnetic interactions in their purest form. Without the noise of a global field, every fluctuation becomes a clue. MAVEN's data provides an almost surgical look into how planetary atmospheres respond to cosmic forces and how vulnerable they truly are. If Earth were ever to lose its magnetic field, it would become another Mars, exposed, stripped, and silent. The red planet is a preview of that fate, a cautionary monument carved by time and magnetism. But it's also a reminder that even broken shields can still react, still echo, still speak. In the end, Mars's fragile magnetosphere may be the reason we detected anything at all. A stronger planet might have absorbed the shock without a trace. But Mars, delicate and scarred, magnified the anomaly for the world to see. It turned an invisible ripple in space into a signal, a clue that something extraordinary had brushed against it. And so, as scientists pore over every byte of MAVEN's recordings, the question deepens. Was Mars's reaction a coincidence, or the faint signature of an interstellar handshake, a brief alignment between two worlds that should never have met? The data remains silent on intent, but the patterns speak volumes. Mars's fragile shield, once thought a weakness, may have become the perfect cosmic sensor, capturing a moment of contact that no other planet could have revealed. MAVEN's watchful eyes orbiting silently above the ruddy wastelands of Mars, NASA's MAVEN spacecraft has become something of a cosmic sentinel. Its instruments the planet's last defense against forgetting its own story. When it was launched in 2013, MAVEN's mission sounded straightforward: to study how Mars lost its atmosphere. But in truth, it became much more than that. MAVEN became a witness, an electronic archaeologist tracing the invisible forces that stripped a once-living world bare. And in late 2025, it witnessed something no one could have predicted. MAVEN's full name, Mars Atmosphere and Volatile Evolution, hints at its purpose. It was built to measure the slow leak of air into space, to monitor the delicate tug-of-war between Mars and the solar wind. Its magnetometer, perched at the end of a long boom to minimize interference, detects even the faintest fluctuations in magnetic fields. Its plasma analyzers sniff the ionized gases that escape the upper atmosphere. Its ultraviolet sensors trace the dance of energetic particles as they excite atoms high above the planet. For over a decade, these instruments have captured the rhythm of Mars' invisible weather, the daily pulses of solar energy, the slow heartbeat of atmospheric erosion. But MAVEN's long watch has also revealed the planet's unpredictability. Every so often, the data shows bursts of activity that seem to defy explanation: waves, oscillations, and magnetic tremors that appear from nowhere and fade into silence. The spacecraft's operators have learned to recognize the usual culprits: passing solar storms, cosmic ray showers, dust interactions. Yet the event following 3 Atlas's flyby didn't match any known pattern. In the hours before the interstellar visitor swept past Mars, MAVEN's instruments recorded calm conditions. The solar wind was steady, its speed averaging 430 kilometers per second. The background magnetic field hovered around 23 nanotesla. The upper atmosphere glowed faintly, as expected, under normal solar radiation. Then, a few hours after 3I Atlas's closest approach, something changed. The magnetometer readings began to fluctuate, small, rhythmic pulses that quickly grew in intensity. Within minutes, the field strength had doubled. The plasma analyzer registered a surge in ion flux, specifically oxygen and carbon dioxide ions, the same species found in Mars's thin atmosphere. It was as if the planet's upper layers were suddenly stirred, electrified from an unseen source. MAVEN's ultraviolet spectrograph saw a corresponding flash of emission, faint but distinct, sweeping across the southern hemisphere. The team on Earth initially suspected a solar anomaly, but cross-referencing with solar observatories showed no flares, no coronal mass ejections, no shockwaves from the sun. MAVEN's own solar sensors confirmed it. The energy wasn't coming from sunlight. It was coming from space itself. For 12 tense hours, MAVEN continued to log data as the anomaly unfolded. The spacecraft's orbit carried it repeatedly through regions of disturbed plasma, each pass revealing new clues. The magnetic field lines were twisted, forming tight curls instead of their usual smooth arcs. Electron densities spiked, suggesting waves of charged particles sweeping through the ionosphere. And most puzzling of all, the direction of the disturbance was wrong. It didn't align with the solar wind flow. It came from a different angle entirely. When analysts plotted that direction against Mars's orbital geometry, the results sent chills through the mission team. The vector pointed almost exactly toward the position of 3I Atlas, not just roughly, but within 2 degrees of its known path. MAVEN's instruments are not designed to track moving objects, but their data can infer where energy enters the system. In this case, all signs led to one improbable conclusion: the disturbance had originated along the trajectory of an interstellar body. Whether by coincidence or connection, 3I Atlas had passed by, and Mars's magnetic environment had flared in response. The first detailed report came from the MAG instrument team, the scientists responsible for the magnetometer. They described a compression event lasting nearly 4 minutes, followed by oscillations that decayed over the next hour. The waveform resembled a shockwave, a magnetic ripple traveling through plasma. But its frequency spectrum didn't match typical solar or atmospheric sources. It looked artificial, not in the technological sense, but in the sense of being geometrically clean, too structured to be random turbulence. The plasma wave analyzer told a similar story. Ions were accelerated to velocities inconsistent with solar wind drift. Some even reversed direction temporarily, as though caught in a loop of magnetic reconnection, a process where field lines snap and reconnect, releasing bursts of energy. Such events can occur naturally, but usually under strong external pressure, like during solar storms. There was no storm that day. There was only 3I Atlas. For days, the MAVEN team debated the possibilities. Could it have been an unrecorded coronal mass ejection traveling on a narrow vector missed by Earth-based instruments? Could cosmic rays from a distant flare have triggered localized ionization? Or could the interstellar visitor itself have carried a magnetic signature strong enough to leave an imprint? None of the explanations felt complete. What made MAVEN's observations even stranger was the precision of the timing. The main surge began 167 minutes after 3I Atlas crossed Mars' orbital plane, the same delay that would occur if a plasma disturbance traveled through the solar wind from the object's position to the planet's magnetosphere. That alignment was too neat to ignore. Inside NASA's Goddard Space Flight Center, where MAVEN's mission control operates, the event became an obsession. Teams ran simulations using the MSFE Mars Solar Wind Flux Exchange model, attempting to recreate the observed waveforms. In most runs, no combination of solar wind parameters could reproduce the sharpness of the compression. Only when they introduced an external, moving magnetic source did the results begin to match. That external source could only be one thing: the interstellar traveler itself. In the speculative model that emerged, 3I Atlas carried a charged plasma sheath formed by its journey through interstellar space. As it entered the heliosphere, that sheath interacted with the solar magnetic field, creating a magnetized wake trailing behind it. When Mars intersected that wake, the residual currents compressed its induced magnetosphere. The effect would be brief, powerful, and perfectly timed with the MAVEN spike. Of course, this remains a hypothesis, a fascinating but unproven link. Yet the elegance of the timing continues to tempt even the most skeptical minds. For MAVEN, this wasn't just another data point. It was history. For the first time, a planetary probe may have recorded direct evidence of an interstellar object interacting with a planet's magnetic field. The discovery, if confirmed, could rewrite our understanding of how alien material influences solar systems they pass through. In the aftermath, MAVEN's logs revealed something subtle but persistent. For nearly 40 hours after the main event, the spacecraft continued to record faint, rhythmic fluctuations, tiny oscillations in the magnetic field repeating every 12 minutes. Some mission scientists called it the echo, others the hum. It might have been instrumental drift or residual plasma oscillations. To those who followed the event from the start, it felt like the ghost of something larger, an after-image of contact between worlds. Data from the European Space Agency's Trace Gas Orbiter corroborated parts of the anomaly. Its instruments detected minor density changes in the upper atmosphere around the same time, confirming that whatever struck Mars affected more than just magnetic fields. Even ground-based infrared telescopes noticed slight thermal variations in the planet's upper layers, consistent with atmospheric heating. For a spacecraft built to study slow evolutionary processes, MAVEN suddenly found itself in the middle of a cosmic event, one that bridged interstellar and planetary physics in ways no one had imagined. Its quiet orbit became the front row seat to an unfolding mystery. Yet MAVEN's watchfulness comes with humility. It doesn't interpret, it observes. It doesn't assume intent, it records. Every byte of its data is now being pored over by researchers from NASA, SA, and multiple universities searching for meaning in the noise. Some see it as the most profound planetary interaction ever documented. Others see it as another reminder of how chaotic plasma physics can be. But deep down, even the skeptics admit there's something haunting about the timing. The odds of an interstellar object passing near a planet and that planet experiencing a magnetic disturbance within hours are astronomically low. To those who've studied space weather their entire careers, the MAVEN readings feel less like coincidence and more like a cosmic message, an accidental transmission written in magnetism. MAVEN remains above Mars, still circling, still listening. Its orbit will decay slowly over decades, but its sensors continue to send back whispers from the planet below and the space beyond. Perhaps someday another interstellar traveler will pass, and MAVEN, or its successor, will be there again to record the encounter. For now, the spacecraft holds its silent vigil, its watchful eyes fixed on a world that trembles at every cosmic touch. The Martian sky has gone quiet again, the plasma fields calm. Yet in the data archives, deep within NASA's servers, lies a record of the night Mars seemed to awaken under an alien influence. A night when MAVEN, the sentinel of a dead world, may have witnessed the first true magnetic handshake between a planet and something not of the solar system. The spike in the data come. At first, no one noticed it. It was buried in a torrent of raw telemetry, numbers scrolling endlessly across monitors at NASA's Goddard Space Flight Center. MAVEN's magnetometer, like a heartbeat monitor for Mars' invisible skin, had been transmitting steady, predictable readings for weeks. 23 nanotesla here, 25 there. Minor variations, the kind you'd expect from the planet's thin, fluctuating ionosphere. But on one specific night, the line on the graph suddenly lurched upward. The data stream spiked, sharply, cleanly, and without warning. Within seconds, the magnetic field strength had doubled, then tripled. The waveform sharpened into a single jagged peak before collapsing just as abruptly. For a moment, it was gone. Then, smaller ripples followed, oscillations repeating every few minutes, decaying gradually like echoes fading down a long metallic corridor. The entire event lasted less than 10 minutes, but in those 10 minutes, Mars' magnetic environment behaved as though something massive had just brushed against it. Analysts first assumed it was an instrument glitch. Spacecraft sensors are notoriously sensitive. Even a minor electrical discharge or software hiccup can create phantom readings. But when engineers ran diagnostics, everything checked out. No memory errors, no interference from MAVEN's other systems. The magnetometer was healthy, and more importantly, other instruments saw it too. The plasma analyzer detected a matching surge in ion density, especially oxygen ions, molecules torn from Mars' thin atmosphere and accelerated upward. The ultraviolet spectrograph picked up a faint glow across the southern hemisphere, suggesting a burst of auroral energy. The correlation was undeniable. This wasn't an instrument error. It was an event. When the team overlaid the timestamps, the synchronization was uncanny. Every sensor aboard MAVEN, magnetometer, plasma detector, ultraviolet imager, registered the disturbance within the same 3-minute window. On a planet that had been magnetically quiet for days, something had just happened that shook its fragile upper layers. The first to notice the anomaly in real time was Dr. Nina Laurent, a space physicist at Goddard specializing in magnetospheric modeling. Reviewing the live telemetry feed that morning, she paused when she saw the spike. At first, she thought it was a data compression artifact, one of those harmless blips caused by packet loss. But when she cross-referenced it with the ion counts, she felt her stomach tighten. The shapes matched too perfectly. She alerted the rest of the MAVEN operations team. Within hours, a small group had gathered around her console, replaying the data again and again. The room filled with the low hum of fluorescent lights and the steady clicking of keyboards. On the monitor, Mars' magnetic profile appeared as a simple graph, a smooth wave punctuated by that single violent peak. What was the sun doing at this time? Someone asked. They checked. Nothing. The solar observatories monitoring X-ray and UV activity showed no flares, no coronal mass ejections. The solar wind was calm and consistent. There was no external driver, no known reason for a magnetic storm. Then someone mentioned 3I Atlas. The interstellar object had passed near Mars only hours before. The timing lined up disturbingly well. At first, everyone dismissed it. The odds were ridiculous. An interstellar body passing through the solar system, somehow influencing a planet magnetically? It sounded like science fiction. But then the data kept refusing to fit any other explanation. Plotting the magnetic vector from MAVEN's perspective revealed the direction of the incoming disturbance. It didn't align with the sun, as normal magnetic storms do. Instead, it pointed roughly 31 degrees off the ecliptic plane, exactly where 3 Atlas's trajectory had crossed Mars's orbit. The discovery rippled through the mission team like a slow, spreading realization. For years, MAVEN had recorded countless magnetic events triggered by solar activity. Every spike, every pulse could be traced back to the sun. But this one broke the pattern. It came from somewhere else, somewhere alien to the heliospheric rhythm. As the investigation deepened, analysts noticed smaller, secondary spikes following the main one. Each was weaker than the last, decaying in amplitude over several hours. These aftershocks suggested that whatever had disturbed the magnetic field had set off resonance waves in the ionosphere, waves that continued to ring long after the initial impact. MAVEN's data log showed that during the main spike, the local magnetic field compressed by nearly 50%. Such a compression would normally require the force of a solar wind shock or CME front. Yet the solar data remained stubbornly flat. The only plausible way to generate such a local effect was through a nearby magnetic disturbance, something passing close enough to interact directly with the planet's induced field. At this point, NASA brought in experts from its Plasma Physics Division. They ran simulations using the Mars Solar Wind Interaction Model, MSWIM, feeding in MAVEN's real-time plasma data. To recreate the spike, they had to inject an external variable, a moving magnetic object cutting through the solar wind at extreme speed. Only then did the simulation reproduce the waveforms observed in the magnetometer data. The result matched almost perfectly if they assumed a transient source moving at around 95 kilometers per second, the recorded velocity of 3I Atlas as it passed Mars's orbit. When this finding was presented to the broader scientific community, it split the room. Some hailed it as possible evidence of magnetic coupling between a planet and an interstellar object. Others dismissed it as coincidence, an intersection of unrelated cosmic noise. But the data itself refused to vanish. The spike was real, and so was its timing. The magnitude of the field change, rising from 25 to 48 nanotesla in under 60 seconds, was unprecedented for a non-solar event. MAVEN's instruments had never recorded such a rapid, isolated surge without corresponding solar input. The waveform was clean, almost too clean, like a signal rather than a storm. That led some researchers to explore a more controversial idea: magnetic induction from the object itself. If 3I Atlas carried even a residual field, perhaps from magnetized material in its core, it could have interacted with the solar wind to create a moving electromagnetic bubble. As it passed near Mars, this bubble could have compressed the planet's induced magnetosphere, generating the spike MAVEN observed. Others proposed an alternative mechanism: dynamic plasma coupling. The idea was that the interstellar object, plowing through the solar wind, might have left a turbulent wake of ionized dust and magnetic eddies. When that wake brushed past Mars, it could have created transient pressure fluctuations, mimicking a magnetic storm. Either way, it required something external, something passing near the planet at just the right moment. While the scientific debate raged, the raw data remained hauntingly beautiful. The magnetometer trace, smooth baseline, sudden spike, rhythmic echoes, looked almost like a heartbeat. In fact, one analyst joked that Mars had flatlined and come back to life. But under the humor, a quiet unease settled over the team. They were staring at something no model had predicted. Later, when MAVEN's orbit carried it through the night side again, the magnetometer picked up faint residual oscillations, tiny pulses exactly 12 minutes apart. The pattern repeated for nearly 40 hours before fading into the background noise. No one could explain it. Some called it a ringing effect in the magnetic field, a resonance left behind after the initial compression. Others wondered if Mars had simply recorded the echo of an interstellar crossing. The spike soon gained an informal name among mission staff: the pulse. It became a whispered shorthand in emails and conference notes. Any update on the pulse? Cross-reference the pulse dataset. It was both scientific and poetic, a single, inexplicable jolt that seemed to say, something passed this way. When the data was finally released to the wider scientific community, the public caught on quickly. Amateur astronomers, conspiracy theorists, and serious researchers alike began poring over the readings. Speculation spread fast. Some claimed it proved interstellar probes might emit electromagnetic signatures. Others suggested it was evidence of charged particle storms linked to exotic matter. NASA, careful as ever, released a restrained statement. MAVEN detected an anomalous magnetic fluctuation of unknown origin coincident with the passage of the interstellar object 3 Atlas near Mars. Behind closed doors, though, the mood was more contemplative. The mission scientists weren't chasing aliens. They were chasing understanding. For them, the spike was not proof of intelligence, but proof of interaction. Proof that interstellar material could leave fingerprints on planetary environments. It was a cosmic handshake, brief, invisible, but measurable. Months later, MAVEN's data continued to reveal subtle patterns hidden within the spike. Fourier analysis showed harmonic frequencies matching those seen during known magnetic reconnection events, suggesting rapid restructuring of field lines. In other words, Mars' magnetic environment hadn't just been compressed, it had snapped and reformed, releasing energy in the process. That detail changed everything, because if the interaction caused reconnection, it meant energy was transferred. Real, measurable power exchanged between an alien object and a planetary field. And that was something no one had ever seen before. Today, the event remains an open mystery in planetary science. The spike stands as both a data point and a symbol, a reminder that the solar system is not an isolated bubble, but a crossroads where travelers from other stars can leave their marks. And for 10 minutes on a quiet night above Mars, MAVEN caught one of those marks, a brief magnetic fingerprint from the void. The numbers may fade on screens, but the story endures. A planet without a shield, a spacecraft built to listen, and a signal that defied the rhythm of the sun. A spike that shouldn't have happened, but did. Plasma surge signatures. When the magnetic spike first appeared in MAVEN's readings, it was startling. But when the plasma data was examined alongside it, the mystery deepened into something almost otherworldly. Mars didn't just experience a magnetic jolt, it experienced a flood of charged particles, an atmospheric surge that rippled through its upper layers like a wave through shallow water. The plasma analyzer aboard MAVEN, technically the solar wind ion analyzer and the superthermal and thermal ion composition static instrument, exists to measure the density, energy, and direction of ions around the planet. It's how scientists trace the invisible currents that strip Mars's atmosphere away grain by grain. Normally, these readings are subtle, gentle variations as the solar wind ebbs and flows. But on that night, they weren't subtle at all. The raw numbers told a story of violence. Within minutes of the magnetic spike, ion densities in the upper atmosphere jumped fivefold. The flux of oxygen ions, atoms stripped of electrons by solar radiation, soared to record highs. CO2 ions spiked too, followed by erratic bursts of lighter hydrogen and helium. The plasma temperature climbed from a calm 2000 Kelvin to nearly 10,000 before falling again just as quickly. No solar event on record had caused such a rapid and isolated surge at Mars. At first glance, the readings resembled a small-scale version of a coronal mass ejection hitting Earth's magnetosphere, a classic shock front followed by plasma turbulence. But the shape of the surge didn't fit the solar profile. Instead of a smooth compression wave, MAVEN detected alternating bands of density and depletion, layered structures that looked like interference patterns. Something had excited the ionosphere into oscillation, as though multiple forces were colliding in rapid succession. To plasma physicists, this was astonishing. Mars' ionosphere is thin and fragile. Its plasma density is only about 1/10,000th of Earth's. To produce oscillations strong enough to register at MAVEN's altitude required an immense but brief injection of energy, something capable of rearranging entire layers of charged gas in seconds. When the MAVEN team ran the event through the Mars ionospheric response model, they discovered the energy input was equivalent to a small solar storm compressed into a single planetary hemisphere. Yet again, the sun was ruled out. The only body in the vicinity capable of producing such localized effects was 3I Atlas, which had passed Mars's orbit less than 4 hours before. The timing fit too perfectly. The interstellar visitor's trajectory crossed the solar wind's downstream region relative to Mars, the so-called magnetotail zone, where solar particles are deflected around the planet like water around a rock. That region acts as a plasma trap, collecting charged particles and storing them temporarily. If 3I Atlas carried even a faintly magnetized sheath, it could have distorted that plasma tail, triggering a backflow of particles into Mars's ionosphere. The data supports this. MAVEN's static instrument detected two distinct plasma streams, one flowing from the usual solar direction and another sweeping laterally from an oblique angle, the same angle corresponding to 3I Atlas's incoming path. The two streams collided near the terminator line, generating turbulence visible in both ion and electron counts. Imagine two winds meeting head-on in the thin skies of Mars. Not air, but electric wind. The collision zone would have erupted with eddies of charged particles, curling like luminous whirlpools in the planet's invisible sea. The magnetometer would record it as a spike, the plasma analyzer as a surge, and the ultraviolet sensors as faint auroral glow. It all fits the signature of a transient plasma storm born not from the sun, but from an alien wake. Some scientists began calling it the surge event. In internal documents, NASA described it as a localized plasma enhancement of unexplained origin. Behind that clinical phrasing was quiet astonishment. For the first time in recorded history, a planet might have been struck, not by solar wind, but by an interstellar plasma front. To understand why this matters, we have to revisit how plasma behaves in space. Unlike neutral gas, plasma is a living thing, a fluid threaded with magnetic fields, capable of carrying and storing energy across vast distances. It can oscillate, spiral, even sing through radio frequencies. When two plasma regions with different properties meet, they don't mix quietly. They resonate, exchange energy, and sometimes explode into instability. MAVEN's readings that night captured all three phases of that interaction: a sudden compression, the spike, rapid oscillations, the interference patterns, and a decaying afterglow of low-frequency plasma waves that lingered for nearly a day. The sequence mirrored what plasma physicists call magnetic reconnection, a process where magnetic field lines snap and rejoin, releasing stored energy as heat and motion. If that's what occurred, then Mars didn't just absorb a passing wave, it reacted to it. The planet's induced magnetosphere may have briefly coupled with the passing magnetic field of 3I Atlas, discharging energy across its upper atmosphere. MAVEN's instruments registered several brief particle jets, thin bursts of accelerated ions shooting upward into space at hundreds of kilometers per second. These jets were aligned almost perfectly along the direction of the interstellar object's trajectory. The implications are staggering. For decades, scientists have assumed interstellar objects were little more than cosmic debris, passive wanderers obeying gravity and sunlight. But MAVEN's plasma data suggests they might also carry invisible charge, shaped by their journey through alien magnetic environments. When such an object passes near a planet, the interaction could be far more dynamic than anyone imagined. One of the more controversial findings came from MAVEN's Langmuir probe, which measures electron temperature and density. During the event, it recorded brief bursts of anomalously low electron density, microcavities forming and collapsing in milliseconds. These are typical signatures of plasma double layers, regions where strong electric fields develop spontaneously between layers of ionized gas. On Earth, they appear during lightning or auroras. On Mars, they may have flared to life under alien influence. Another anomaly. The radio instrument detected a faint hiss of electromagnetic emissions between 2 and 3 kilohertz, lasting just under 8 minutes. When converted to audio frequencies, it produced a rising, undulating tone, hauntingly similar to the auroral chorus sounds Earth's magnetosphere emits during geomagnetic storms. But this time, the source was Mars, a planet thought too weakly magnetized to sing. That eerie signature might be the most direct evidence yet that Mars experienced a true plasma storm, however brief. Some have even suggested that the wave pattern in the radio hiss encodes the same periodicity as the object's own tumbling rotation, an impossible coincidence unless the two were somehow linked. In the months that followed, scientists pored over MAVEN's data archive, comparing the surge event to every recorded magnetic and plasma disturbance since the mission began. None matched. Not even the most violent solar storm of 2017 produced the same combination of magnetic compression, plasma density, and radio emission. The pattern was unique, a fingerprint from beyond the solar system. Skeptics, of course, urged caution. Correlation is not causation. The plasma surge could have been a coincidental overlap of local processes, perhaps a spontaneous ionospheric instability amplified by natural resonance. But even those skeptics admitted that the geometry was uncomfortably precise. To have two plasma streams intersect at the same moment an interstellar object passed within 3 million kilometers of Mars would require statistical odds bordering on the absurd. For those who study planetary magnetism, the event has become a case study in cosmic coincidence, or cosmic connection. It challenges the assumption that planets are passive objects influenced only by their stars. Instead, it hints at a universe far more interactive, where even a passing fragment from another system can awaken dormant energies in a planet's sky. In private correspondence, one MAVEN scientist described the plasma data in poetic terms. It's as if Mars took a deep breath when the object passed, and for a few minutes, the air itself remembered electricity. That line circulated quietly among researchers, not because it was scientific, but because it captured the awe of the moment, when cold numbers transformed into something resembling communication between worlds. In the end, MAVEN's plasma instruments recorded something unprecedented, a structured surge of ionized matter consistent with an external magnetic disturbance. Whether 3I Atlas caused it directly or merely coincided with it, the event stands as a reminder that space isn't empty. It's alive with invisible tides, ready to respond to even the smallest touch. If the interstellar visitor truly disturbed Mars's plasma shield, it would mark the first documented evidence of an extrasolar body influencing a planet's space weather, a handshake written not in light or gravity, but in the raw language of plasma itself. And so, the data remains, archived and dissected, yet never fully explained. In the silent vaults of NASA's servers, the numbers still hum faintly. The digital echo of the night Mars shimmered with borrowed electricity. Some call it coincidence, others a clue to deeper cosmic design. But to those who've studied the surge frame by frame, it feels like a message whispered in the only voice space has ever known. Charged particles in motion, briefly aligned by something that came from the stars, solar storms versus local disturbance. For as long as we've studied Mars, nearly every major magnetic or plasma anomaly has had one familiar culprit: the sun. Solar storms, coronal mass ejections, and gusts of high-speed solar wind are the architects of chaos across the inner planets. They hurl charged particles at worlds without mercy, compressing magnetospheres, igniting auroras, and stripping atmospheres. MAVEN's mission was built on that premise, to observe how the sun eats away at Mars over time. Yet in late 2025, as data poured in from the so-called surge event, something didn't fit. The fingerprints of the sun were missing. Every known solar storm leaves a signature, a chain of observable clues. It begins with a flare, visible in ultraviolet and X-ray. Then, minutes later, satellites detect a pulse of energetic particles racing ahead of the main shock. Hours after that, the heavy plasma cloud arrives, hammering planetary fields in a predictable pattern of compression, rebound, and decay. Earth sensors catch it. SOHO and stereo satellites record it. The rhythm of solar violence is precise, like a heartbeat the cosmos has long since memorized. But in the MAVEN data, there was no such prelude. The spike and plasma surge erupted in isolation, as if Mars had been struck by something that came from a completely different direction. The first question every scientist asked was simple. Was there a hidden solar storm? Maybe a narrow coronal jet missed Earth's sensors but clipped Mars instead. The team scoured heliospheric data from every available source: NASA's Parker Solar Probe, the Solar and Heliospheric Observatory, the European Solar Orbiter, and ground-based telescopes monitoring the sun's disk. Nothing. The sun's activity during that window was unusually quiet. Solar flux was stable, proton counts were low, and no Type 2 or 3 radio bursts, the telltale screams of solar eruptions, were detected. Solar weather models, such as ENLIL and WSA-ENLIL, were run backward, reconstructing the state of the solar wind during the event. Even when researchers pushed the parameters to extremes, no simulation could produce a shock front that would reach Mars at the right time. The heliospheric current sheet was calm. There were no transients, no pressure waves, no missing data gaps large enough to hide a storm of that magnitude. The sun, for once, was innocent. So if not the sun, what else could it be? Mars does experience local disturbances, magnetic hiccups born of its own fragile environment. Dust storms, for example, can generate static electricity through friction, creating small electric fields that occasionally pulse upward into the ionosphere. But MAVEN has observed these countless times, and they look nothing like what was recorded. Dust-generated electric fields affect the lower atmosphere and produce slow, low-frequency oscillations. The surge event, by contrast, originated high above the surface and moved at speeds close to the ion acoustic limit, hundreds of kilometers per second. Another possible source was a transient interaction between Mars' crustal magnetic fields and the solar wind. When the solar wind's direction shifts suddenly, it can cause magnetic reconnection events near these localized field regions. But again, that requires a solar trigger, which wasn't present. The MAVEN data showed the disturbance came from a vector misaligned with the sun entirely, roughly 31 degrees off the ecliptic plane, matching the track of 3I Atlas. The more the team compared the two possibilities, solar versus local, the clearer the distinction became. Solar storms produce large-scale, symmetric compression of the magnetosphere. Local events, by contrast, are patchy, confined, and short-lived. The surge event had both signatures at once, a global magnetic compression lasting minutes, but with local plasma turbulence focused on one hemisphere. It was as if Mars had been struck by a directed energy pulse, not a sweeping solar wave. For days, scientists argued in message threads and late-night conference calls. Could a rogue solar filament have erupted unnoticed from the sun's far side, its shockwave sneaking through an unmonitored corridor? Or was this truly something else, something local yet external, like a passing object's wake? Dr. Rami Ishikawa, a plasma physicist from JAXA, collaborating with the MAVEN team, proposed an intriguing middle ground, a hybrid disturbance. In his model, 3I Atlas, moving through the heliospheric magnetic field, could have acted as a conductor, briefly channeling solar current through its ionized envelope and releasing it downstream like a pulse. The result would mimic a miniature solar storm, but without a flare or CME. Think of it, he wrote, as a ghost storm, born of the sun's energy, but carried by something else. The math supported the idea. Calculations showed that if the object carried even a weak magnetic field on the order of a few microtesla, it could distort the local solar wind flow around it, creating a bow shock similar to a tiny magnetosphere. As that magnetic bubble passed near Mars, the planet's own induced field could have resonated with it. The resulting interaction would generate exactly the kind of oscillating compression MAVEN observed. Still, the skeptics persisted. NASA's own heliophysics division urged restraint, reminding everyone that extraordinary claims require extraordinary proof. Without direct evidence linking the timing to 3 Atlas's position, the team risked attributing random noise to coincidence. Yet every attempt to find an alternative source failed. There were no upstream solar wind anomalies detected by the Mars Express spacecraft, no proton events, no spikes in radiation, no visible auroras on Earth or Venus, which would have been hit if the sun were to blame. Then came another piece of evidence, the direction of the ion jets. MAVEN's static instrument detected accelerated ions streaming not sunward but tangentially, sideways relative to Mars's orbital motion. That alone ruled out a solar origin. Solar storms always push plasma toward the sun-facing side of the planet. These flows came from the flank, like the wake of something sweeping by. In one internal report, a NASA analyst summarized it bluntly: no solar correlation, directional flow inconsistent with CME, disturbance likely local and transient, external source unknown. That phrase, external source unknown, became the hallmark of the event, because for all the careful analysis, there was one truth no one could ignore. The moment the interstellar object passed Mars's orbit, the red planet reacted. Historically, scientists have struggled to separate solar influence from other cosmic factors. The sun dominates everything. Its presence overwhelms subtle interactions. But this event offered something new, a rare moment when the sun's quietude provided a blank slate. In that silence, the universe whispered something else. When data from the European Space Agency's Trace Gas Orbiter was later integrated, it confirmed that the upper atmosphere of Mars had briefly heated by nearly 10 degrees Kelvin during the spike, again with no solar flux increase. To generate that heat, energy had to be injected from space, not from below, and the only active variable in the region was 3I Atlas. The debate eventually settled into two camps. The solar traditionalists argued that some undetected heliospheric irregularity, a stealthy magnetic flux rope or micro-CME, must have struck Mars. The localists, led by MAVEN's younger analysts, maintained that the geometry and timing were too perfect to ignore. To them, 3I Atlas wasn't a passive wanderer, it was a catalyst, the match that ignited an invisible circuit connecting Mars, the solar wind, and the interstellar medium. To test both ideas, computational models were run through NASA's Helioswarm SimLab, an advanced plasma simulator capable of mapping multi-body interactions in 3D. The results were stunning. When 3I Atlas was omitted, no model produced a surge. When inserted, with an assumed conductive plasma tail roughly 1,000 kilometers long, the simulation reproduced nearly every observed feature. the magnetic compression, the plasma oscillations, even the direction of ion flow. That simulation didn't prove causation, but it painted a compelling picture. An interstellar object dragging its own magnetic wake across the Martian bow shock, stirring a ghost storm that mimicked the fury of the sun. If true, it challenges how we define solar weather. Perhaps what MAVEN recorded wasn't solar at all, but a new class of space event, one born from the meeting of two magnetic systems, one planetary, one alien. A localized, non-solar plasma coupling that temporarily energized an entire world. The ramifications stretch beyond Mars. If a single interstellar fragment can disturb a planet's magnetosphere, what could larger or denser visitors do? Could such interactions influence climate, erosion, or atmospheric chemistry? Could they leave magnetic scars detectable millions of years later? These are no longer idle questions. They're the frontier of planetary astrophysics. For now, the MAVEN team remains careful. Officially, they call it a localized disturbance event. Unofficially, some call it the visitor's storm. A storm without lightning, without clouds, without origin. A magnetic heartbeat felt across the Martian sky. And somewhere in that red silence, as MAVEN continues its orbit, the instruments keep listening, waiting for the next anomaly. Because if the surge event truly was not solar, then Mars may have just revealed a hidden dimension of cosmic weather. Storms carried not by the sun, but by travelers from the stars themselves. Mirror modes and instabilities. When scientists first overlaid MAVEN's magnetic field data with its plasma wave readings, they noticed something subtle, something that didn't look like a single clean pulse from a passing storm. The waveform wasn't smooth. It was patterned, rippling in and out with near-perfect periodicity, like the steady beat of a drum echoing through thin air. That pattern had a name in plasma physics: mirror modes. And on Mars, it was the first time they'd ever been recorded so clearly. Mirror modes are the fingerprints of instability. They appear when a plasma, an electrically charged gas, is out of balance. In simple terms, when the pressure of the magnetic field and the pressure of the particles within it don't agree, the plasma begins to oscillate. It forms wave-like structures, magnetic bubbles and holes that expand and contract in rhythmic bursts. They are the plasma equivalent of turbulence, but on a cosmic scale. Usually, mirror modes around Mars are subtle, the result of minor solar wind variations. But the MAVEN data from the 3I Atlas event showed something far more dramatic. These waves were stronger, more coherent, and sustained for longer than any natural solar fluctuation should have allowed. They repeated every 90 seconds for nearly 40 minutes, enough time for MAVEN to complete half an orbit and confirm that the pattern wasn't an artifact. The entire ionosphere seemed to be breathing. The key to understanding mirror modes lies in their trigger. They occur when the plasma beta, the ratio of particle pressure to magnetic pressure, exceeds unity. In other words, when the motion of particles overwhelms the magnetic field trying to confine them. This happens when fresh energy is dumped into a plasma faster than the magnetic field can redistribute it. The source of that energy is what defines the event. On Earth, mirror modes often follow geomagnetic storms. On Jupiter, they come from volcanic plumes on Io pumping ions into the planet's magnetic field. But on Mars, in late 2025, there was no volcano, no storm, and no internal source, only the passing of an interstellar visitor. The MAVEN team began modeling possible triggers. They knew the sun was quiet. They also knew the surge in plasma density coincided with the mirror mode pattern. That meant the instability began right after the ion influx, not before. Something had injected high-energy particles into Mars's ionosphere, fast enough to raise plasma pressure, but not to destroy the coherence of the wave. That ruled out chaotic turbulence. It pointed instead to a structured disturbance, a magnetic field interacting with Mars's induced magnetosphere in a steady, organized way. If that sounds like science fiction, it's not. Space physicists have long theorized that magnetized bodies, whether comets, spacecraft, or asteroids, can generate mirror mode turbulence when they move through plasma environments. The object acts as a moving obstacle, distorting field lines and leaving behind oscillations in its wake. The strength of those oscillations depends on the relative velocity and magnetic contrast. At 95 kilometers per second, 3I Atlas was moving faster than any comet ever recorded near Mars. Even a small residual field around it could have amplified those distortions dramatically. The most intriguing part of the MAVEN data was the asymmetry. The mirror modes weren't uniform across Mars's magnetic field. They were concentrated over the southern hemisphere, specifically above a region known as Terra Serenum, home to some of the strongest crustal magnetic anomalies on the planet. These ancient magnetic scars, remnants of Mars's long-dead dynamo, act like amplifiers. When an external magnetic fluctuation passes overhead, they trap and echo it, extending its lifespan. That explained why the waves persisted for nearly an hour. Own buried magnetism had turned into a resonant chamber, catching the incoming pulse and ringing with it like a giant tuning fork. MAVEN's sensors, sweeping through that region again and again, recorded the decay curve in exquisite detail, each oscillation slightly weaker than the last, each period stretching as the plasma cooled. It was, in every measurable way, the signature of a mirror mode cascade. Still, one question haunted the team. How could a transient interstellar object produce such ordered instabilities in a planetary plasma? To answer that, they turned to analogs. In the late 1980s, spacecraft passing through Earth's magnetosheath, the turbulent region just outside our magnetic field, had detected mirror modes after interactions with small cometary plasma tails. Those tails, composed of charged dust and ionized gas, carried weak magnetic fields that could couple with the solar wind. The resulting instabilities propagated along field lines and into the magnetosheath, creating oscillations that persisted for hours. The parallel was uncanny. Replace Earth's strong magnetosphere with Mars's fragile one, and replace a small comet with a fast-moving interstellar body, and the physics lined up perfectly. The MAVEN data even showed the same anti-correlation between magnetic and plasma pressure that defines mirror modes. When the magnetic field strengthened, plasma density dropped, and vice versa. The dance was unmistakable. But there was something else, something even more perplexing. The phase velocity of the waves, the speed at which they propagated, was higher than expected. Mirror modes usually travel at a few tens of kilometers per second. These moved at over 200 French. That suggested either an unusually high plasma temperature or a coupling mechanism injecting extra energy into the system. If 3I Atlas carried a magnetized sheath moving at near hypersonic speeds through the solar wind, it could easily supply that extra energy. The object's motion itself might have driven the instability, turning the Martian ionosphere into a reactive layer. One simulation, run by a European Space Agency team collaborating with NASA, showed that if an external magnetic dipole intersected Mars-induced magnetosphere at a shallow angle, it could trigger precisely the oscillations MAVEN observed. The amplitude, wavelength, and decay rate matched within 5% of the real data. It was like dropping a tuning fork into a bowl of water, one researcher said. The whole system vibrated, then settled. To the MAVEN scientists, it meant one thing. The mirror modes weren't random noise. They were evidence of a structured interaction, Mars's plasma responding to an external magnetic pulse in a measurable, predictable way. For planetary science, this was a revelation. Mars had always been considered too weakly magnetized to sustain long-lived plasma instabilities. Its induced magnetosphere is thin and variable, forming and collapsing with every gust of solar wind. Yet here it was, behaving like a fully dynamic system, resonating, oscillating, and releasing energy as though it remembered what it once was, a planet with a living magnetic heart. As researchers examined the energy budget, they found something even stranger. The total energy released during the mirror mode oscillations exceeded what could be accounted for by local sources. It was as if the system had absorbed and re-emitted more energy than it initially received. This led to wild speculation. Could 3I Atlas have carried an oscillating electromagnetic field of its own, one capable of inducing resonance in Mars' plasma at specific frequencies? If so, it might mean the interstellar object wasn't just reactive, but active, carrying a coherent field imprinted during its journey through deep space. No one dared publish that idea outright, but in internal discussions it lingered, a whisper that perhaps 3I Atlas wasn't entirely inert. Not artificial, not alive, but magnetically dynamic in a way that defied conventional cometary behavior. As the mirror modes faded, MAVEN continued to detect faint magnetic fluctuations for nearly 2 Martian days. Even after the main surge had ended, The ionosphere refused to settle completely. Every few hours, a weak echo appeared in the data, tiny ripples barely measurable, like residual vibrations in a bell long after the strike. It was as if Mars itself had become part of a larger cosmic instrument, struck once by a passing hand, then left to hum quietly under the stars. When MAVEN's findings were presented at the 2026 Lunar and Planetary Science Conference, the session was standing room only. Some attendees called it the discovery of the decade, a real-time observation of magnetic instability driven by an interstellar object. Others remained skeptical, arguing that unseen solar variations or instrument crosstalk could mimic mirror modes. But as more independent teams analyzed the data, the consensus slowly shifted. The symmetry of the oscillations, the spatial coherence, the alignment with crustal anomalies, all pointed to a genuine physical phenomenon. One of the final figures shown at the conference displayed a spectrogram of the event. Bright bands pulsing across the frequency spectrum, like evenly spaced and fading into silence. The caption reads simply, "Mirror Mode Resonance, Mars 2025." Beneath it a note, "Trigger source, uncertain. Uncertain, yes, but not without meaning. For in that uncertainty lies the beauty of the unknown, the realization that even a planet stripped of its magnetic soul can still respond to the touch of the cosmos." The mirror modes remind us that the universe is not static. It listens and replies in vibrations and harmonics. For Mars, the passing of 3I Atlas was not merely a near encounter. It was a moment of remembrance, a reminder that deep within the red dust and fractured magnetism, the planet can still sing when struck by the right frequency. And somewhere in the cold, endless dark, 3I Atlas moves on, leaving behind a faint resonance in the data. And perhaps, just perhaps, the first measured conversation between an interstellar traveler and a world once alive with magnetism, Bow-shock dynamics. To understand what truly happened during the 3I Atlas event, scientists had to look beyond the magnetic and plasma anomalies and focus on where they occurred. All the evidence, from MAVEN's magnetometer spikes to its plasma surge data, pointed to a single invisible frontier surrounding Mars, the Bow-shock. In the vast emptiness of space, there is no atmosphere in the traditional sense, but there is wind, solar wind. It races outward from the sun at hundreds of kilometers per second, a constant stream of charged particles threading through magnetic fields. When that supersonic wind encounters a planet, it can't simply pass through. It has to slow down and divert. The result is a shock front, an invisible, curved boundary that forms upstream of the planet like the rippling bow wave of a ship moving through water. For Earth, this magnetic bow shock sits thousands of kilometers from the surface, shaped by the strength of our global magnetic field. For Mars, however, it's fragile and unstable, because the planet's own magnetism is patchwork, remnants of a long-dead core dynamo. Instead of a strong, steady shield, Mars has an induced magnetosphere, a temporary magnetic envelope formed by the interaction between the solar wind and its ionosphere. The bow shock here is thin, chaotic, and prone to collapse. It's within this volatile boundary that MAVEN recorded the most startling data of the entire event. At 4:16 UTC on the night of the surge, MAVEN passed directly through Mars's subsolar bow shock region, the point where the solar wind first collides with the induced field. The magnetometer readings spiked sharply, showing an increase in field strength from 23 to nearly 50 nanotesla. The plasma analyzer detected a simultaneous rise in ion density, but also a strange secondary component, ions moving in directions inconsistent with the solar wind. Some were flowing backward toward the planet. This wasn't normal compression, it was reversal. In simple terms, it looked as though Mars's bow shock had briefly inverted. That concept baffled scientists. The bow shock isn't supposed to reflect particles toward the planet. It's a barrier that deflects them away. For reversal to occur, something must have compressed the shock from behind, an external disturbance forcing plasma into the boundary layer from an unexpected direction. When researchers plotted MAVEN's orbital path relative to 3I Atlas's trajectory, the alignment was uncanny. The interstellar object's projected magnetic wake would have swept directly across the bow shock at roughly the same time the spike occurred. It was as if the visitor's magnetized sheath had grazed Mars's invisible frontier, compressing it like a wave striking a wall of smoke. To confirm, the team ran magnetohydrodynamic MHD simulations, a numerical recreation of how plasma and magnetic fields interact. They used data from both MAVEN and the European Trace Gas Orbiter to define the state of the Martian magnetosphere just before the anomaly. When they added a fast-moving magnetic disturbance, modeling 3I Atlas as a small but conductive body wrapped in a charged envelope, the results were extraordinary. The simulation showed a sudden narrowing of the bow shock, followed by reflected plasma waves traveling planetward. The geometry matched MAVEN's data almost perfectly. The implications were staggering. Mars' bow shock, normally a passive shield sculpted by the sun, had briefly become an active participant in a larger interplanetary interaction. It was no longer simply deflecting solar wind, it was resonating with something external. To understand just how unusual that is, it helps to picture the bow shock as a living membrane. Under normal conditions, the solar wind compresses it gently, maintaining a steady equilibrium. But when a sudden disturbance hits, a solar flare for instance, the membrane ripples and rebounds. MAVEN had recorded such reactions dozens of times. The difference here was that the ripples didn't match solar directions or timing. The pressure waves seemed to arrive laterally, sliding in from an angle, exactly the path 3I Atlas would have taken as it crossed Mars's orbital plane. Some scientists began to describe the event as a side swipe. The object hadn't hit Mars directly, but its passing field may have brushed the edge of the planet's induced magnetosphere, compressing the bow shock asymmetrically. For a few moments, the entire system shifted orientation. Its normal sunward bulge twisted sideways before rebounding to its original shape. MAVEN's instruments recorded the consequences in exquisite detail. Plasma velocity dropped sharply, then oscillated, indicating a rebound wave. Magnetic field lines twisted into helical structures known in plasma physics as flux ropes, tightly wound bundles of magnetism that form when two magnetic fields interact and reconnect. These flux ropes raced across Mars' magnetosheath, carrying bursts of energy that dissipated over the next hour. Flux ropes are rare on Mars. They've been observed before, but always during strong solar storms. Seeing them form during a period of solar quiet was unprecedented, and yet their existence made perfect sense if the bow shock had been forced into temporary overdrive. When two magnetic environments collide, reconnection can occur. Magnetic lines from one field snapping and joining with another, releasing energy in the process. It's the same mechanism that powers solar flares. On that night, the same physics may have played out between Mars and the passing magnetic wake of an interstellar object. The bow shock became a crucible, fusing solar, Martian, and alien magnetism into one explosive interaction. What made this even more eerie was how quickly the system recovered. Within 20 minutes, the magnetosphere relaxed back to its pre-event configuration. MAVEN's sensors showed the field strength tapering off smoothly, as if the planet had exhaled. The bow shock, however, didn't settle quietly. For hours afterward, small ripples continued to propagate through the magnetosheath, each one weaker than the last. It was as though Mars's shield remembered being touched and couldn't quite forget. When the data was presented at the Johns Hopkins Applied Physics Laboratory, one analyst pointed out something extraordinary. The bow shock's oscillation frequency, measured in hertz, matched the expected resonant frequency of the interstellar object's wake if it were magnetically aligned. In other words, Mars had responded at exactly the right pitch to the disturbance. The analogy wasn't lost on anyone. It's as if Mars was tuned to the frequency of 3I Atlas, another researcher commented quietly. Such language skirts the edge of speculation, but the numbers don't lie. The bow shock behaved like a resonator, amplifying the alien signal before releasing it in a burst of plasma turbulence. The total energy transferred was small, equivalent to a moderate solar gust, but the precision of the timing defied randomness. NASA's Heliophysics Division convened a cross-agency review to test the findings. Could the bow shock inversion be a numerical artifact? Could MAVEN have misinterpreted internal noise as external compression? After exhaustive cross-referencing, the answer was no. Every independent instrument confirmed the same thing: a sudden increase in plasma pressure, magnetic twisting, and field realignment, all occurring without any corresponding solar trigger. That left only two explanations. Either Mars had spontaneously generated a magnetic storm from within, physically impossible given its lack of a global field, or it had been struck by something external but local. The latter fit every observable fact. The incident gave birth to a new phrase in the planetary science community: localized bow-shock coupling. It describes what happens when a moving magnetic source interacts briefly with a planetary plasma environment, creating a transient exchange of energy. It's theoretical, almost untested, but after the 3I Atlas encounter, it's become a hot topic in astrophysical modeling. If confirmed, it would mean interstellar visitors can briefly modify planetary magnetic boundaries as they pass, a kind of electromagnetic footprint left in their wake. MAVEN's data suggests that the bow shock during this event compressed by nearly 20%, the largest non-solar deformation ever recorded. In the dense southern hemisphere magnetosheath, the compression may have briefly increased atmospheric loss, accelerating ions into space at twice their usual escape velocity. It's a reminder that the Martian atmosphere, already tenuous, can still bleed energy into the void under the right conditions. As weeks passed, the idea of the bow shock handshake between Mars and 3I Atlas spread beyond technical circles. Popular science outlets described it as a cosmic collision without contact, a brush between two invisible fields that never physically touched. And in some ways, that poetic phrasing isn't far from the truth. The bow shock is where Mars meets the universe, its skin, its pulse, its outermost breath. For a few minutes on that night, something from beyond the solar system brushed that skin, and the planet reacted. It rippled, it twisted, it remembered. When MAVEN completed its next orbit, the field had calmed, the plasma had cooled, and the bow shock had resumed its silent vigil. But deep within the spacecraft's data archives, the memory remains, the unmistakable trace of an interaction that shouldn't have happened, captured in a series of peaks, troughs, and waves. A record of Mars's magnetic frontier trembling beneath an interstellar wind. The bow shock is no longer just a barrier, it's a storyteller, and what it whispered that night, in the language of magnetism and plasma, may be the first direct message ever exchanged between a planet and something not born of this sun. Magnetic field anomalies. Long after the plasma surge subsided and the bow shock regained its shape, something strange continued to linger around Mars. Subtle, persistent distortions in its magnetic field that refused to fade. MAVEN's magnetometer kept detecting low-frequency fluctuations long after the event had supposedly ended. To most of the team, this was noise. But to a handful of planetary physicists who understood the delicate nature of Mars' magnetic skeleton, it was something far more intriguing, an echo that shouldn't exist. Mars, unlike Earth, doesn't possess a global, self-sustaining magnetic field. Instead, its magnetism is fossilized, locked into ancient rocks scattered across the crust. These localized regions of magnetization, concentrated mostly in the southern hemisphere, behave like magnetic islands floating in a sea of plasma. Each is weak on its own, but collectively, they form an intricate patchwork network that occasionally traps charged particles and generates mini auroras. It's one of the reasons Mars is such a perfect, natural laboratory for studying magnetic anomalies. Its system is both fragile and hypersensitive, amplifying even the slightest cosmic disturbance. When MAVEN recorded the bow shock compression and plasma surge during the 3I Atlas flyby, it was expected that those crustal fields would twitch briefly, distorted by the passing energy. But what wasn't expected was how long the twitch would last. Days after the initial surge, MAVEN's instruments continued to measure small but coherent deviations, micro-fluctuations repeating with uncanny regularity. They pulsed roughly every 3 hours, as if the planet were still ringing from the encounter. The first clue came from MAVEN's orbit over Terra Serenum, one of the most magnetically intense regions on Mars. The spacecraft recorded localized field enhancements of up to 15% over the background crustal strength, significant enough to suggest external interference. But there were no active solar conditions, no geomagnetic storms, and no internal sources to account for the change. When plotted spatially, these anomalies formed a curious shape, a long, narrow band stretching across southern latitudes, roughly parallel to the path 3I Atlas would have traced across the planet's orbital plane. It looked, to the astonishment of the analysts, like a magnetic footprint. One NASA geophysicist, Dr. Irene Gorski, described it in her field report as a transient magnetic scar, something that seems to have imprinted upon the crustal anomalies themselves. Of course, Mars's magnetic crust isn't active enough to record new magnetization, but the idea wasn't as far-fetched as it sounded. The energy from a passing plasma wave could temporarily align or distort existing field domains, creating measurable short-term anomalies that slowly relax back to their original states. MAVEN had documented such reorientations before, but never across such a large area, and never with such symmetry. This footprint, if that's what it was, extended nearly 1,200 kilometers, spanning multiple crustal provinces. Even more bizarrely, it appeared to migrate slightly over time. Each MAVEN pass detected the same structure, but shifted a few degrees westward, as if it were drifting with the solar wind. That suggested it wasn't locked to the surface, but suspended above it, perhaps a residual loop of magnetized plasma caught in orbit around the planet. When researchers analyzed the data through spectral decomposition, they found that the anomaly carried multiple harmonics, distinct frequencies of oscillation. The primary mode corresponded to the standard induced field resonance of Mars, but the secondary modes didn't match anything known. They were slightly higher, suggesting an external driver with its own magnetic rhythm. Some speculated these harmonics might have originated from the interstellar object itself. If 3I Atlas possessed a rotating magnetic dipole or an ionized tail with internal currents, those could have imprinted their fingerprint onto Mars's field during the brief interaction. For decades, scientists have debated whether interstellar bodies could retain magnetization from their parent systems. In principle, if an object formed near a magnetized star or passed through dense plasma regions between stars, it could accumulate trapped magnetic flux. Normally, that field would decay after millions of years. But if the body periodically recharges through solar exposure or plasma interaction, remnants could survive. What MAVEN saw might have been the first empirical hint of that theory. Yet skepticism persisted. Could these anomalies simply be artifacts of MAVEN's orbit, or measurement errors caused by changing spacecraft orientation? NASA engineers cross-checked the data using readings from multiple instruments: the magnetometer, the ion analyzer, and even the accelerometers used to detect tiny gravitational tugs. All told the same story: a real external field distortion. The anomalies were spatially correlated with regions of crustal magnetization but did not perfectly overlap, implying that whatever distorted them interacted not with the crust itself, but with the induced magnetosphere hovering above it. In other words, it wasn't geological, it was atmospheric. A ghostly magnetic ribbon floating above the southern hemisphere, visible only to MAVEN's sensitive instruments. To test whether such a structure could persist, simulation teams at the University of Colorado ran magnetohydrodynamic models of Mars's induced field interacting with a fast-moving magnetic disturbance. The results were astonishing. When a magnetized object passed within several million kilometers of the planet, it created a secondary field loop that could linger for days, sustained by charge separation in the upper ionosphere. That lingering loop would drift slowly westward as the solar wind carried it away, matching MAVEN's observations exactly. If true, Mars might have briefly worn an artificial halo, an induced magnetic eddy born from the passing of 3I Atlas. That halo could explain another strange feature recorded during the days following the event: irregular electron precipitation in the southern ionosphere. Normally, electrons spiral along magnetic field lines toward the planet's poles, but MAVEN's detectors found dense clusters appearing at mid-latitudes, where no strong fields should exist. It was as though invisible magnetic tunnels had formed temporarily, guiding particles into regions that should have been magnetically dead. Those tunnels corresponded precisely with the migrating anomaly band. As the band drifted, so too did the electron precipitation zones. The entire system behaved like a moving magnetic conduit, an artificial auroral ring gliding around the planet. MAVEN's ultraviolet spectrometer even detected faint glows corresponding to those areas, lasting minutes at a time before fading. In essence, Mars had developed a transient auroral belt where none should exist. For planetary scientists, this was profound. The red planet, normally quiet and predictable in its weak magnetic behavior, had suddenly demonstrated dynamic magnetism, a level of responsiveness previously thought impossible for a world without a core dynamo. It was as if something external had played its magnetic remnants like an instrument. NASA's internal review labeled the event MFE 2025A, Magnetic Field Event A. The official summary was cautious. Transient magnetic field anomaly coincident with passage of interstellar object 3I Atlas. Potential non-solar interaction, further analysis required. But among researchers, excitement buzzed beneath the restraint. If this was indeed a measurable imprint left by an interstellar field, it would be the first known case of cross-system magnetic coupling, a cosmic handshake between a planetary remnant field and an object born under another star. Over the following weeks, as the anomaly decayed, MAVEN's readings gradually returned to normal. The last traces vanished after about 12 sols. Yet even as the field calmed, faint asymmetries persisted, minute variations in the background magnetic noise. Some speculated these were residual alignments, faint memory zones within Mars's crust, slightly reoriented by the interaction. Geophysicists compared it to remnant magnetization on Earth's oceanic floor, records of magnetic reversals frozen in basalt. But here, the process might have occurred not over millions of years, but in a matter of hours. A planetary-scale magnetic rewrite, temporary but real. For those who believe in coincidence, it was nothing more than an odd but natural oscillation. But for others, the timing, geometry, and persistence of the anomaly painted a different picture. Mars had been marked, however briefly, by something not of this solar system. The idea may sound poetic, but it is grounded in data. The field distortions, the plasma harmonics, the electron tunnels, all aligning with the trajectory of 3I Atlas. Every piece of evidence formed a mosaic of interaction, subtle but undeniable. In the grander sense, the anomaly serves as a reminder of how magnetic fields act as the universe's memory, recording encounters that eyes will never see. Long after 3I Atlas vanished into the inner solar system, its influence remained encoded in the magnetic scars of a silent planet, whispering across MAVEN's instruments. Perhaps someday, when the next interstellar traveler passes by, Mars will react again. Its crustal anomalies twitch faintly like old strings struck by a familiar note. For now, all that remains is the record of that night in 2025, when a dead planet briefly came alive with magnetic song. A song traced not to its sun, but to a wanderer from beyond it, an imprint written in the invisible geometry of magnetism, and a haunting reminder that even silence can leave a resonance in the dark. Interstellar Field Hypothesis. The data left behind by the 3I Atlas encounter told a story that defied the usual logic of solar physics. Every analysis of the magnetic spike, the plasma surge, the bow shock compression, the mirror modes, and the drifting anomaly pointed to an external field that behaved neither like the Sun's nor Mars's. The question was no longer what happened, but what caused it. And so, out of scientific curiosity and quiet disbelief, the MAVEN research team began to explore a theory that until then had belonged more to speculative astrophysics than planetary science: the interstellar field hypothesis. At its core, the hypothesis proposes something simple yet profound: that 3 Atlas was not just a passive traveler drifting through the solar system, but a magnetically active body. Not in the sense of an artificial machine or an alien artifact, but as a natural conductor, a vessel carrying remnants of magnetic structure from the interstellar medium itself. Interstellar space, contrary to its name, is not empty. It's a vast ocean of ionized gas, threaded with magnetic fields that stretch between stars. These fields are weak, measured in mere nanoteslas, but they shape the behavior of cosmic rays, the formation of nebulae, and the evolution of entire star systems. When an object drifts through that ocean for millions of years, it doesn't emerge untouched. Its surface becomes charged, its internal structure polarized, and its surrounding plasma sheath imprinted with magnetic geometry. That's what 3I Atlas might have carried: a frozen remnant of a field from beyond the heliosphere. For decades, astronomers have debated whether such interstellar relics could survive long enough to enter another solar system. The challenge lies in scale. When a foreign object enters the heliosphere, the sun's magnetic field, known as the heliospheric current sheet, should dominate, erasing or reorienting any residual charge. But MAVEN's data suggested otherwise. The field anomalies near Mars were not aligned with the solar wind or the heliospheric field. They were tilted, skewed by roughly 31 degrees, exactly matching the inclination of 3 Atlas's inbound path. It was as though the object carried its own magnetic signature, strong enough to resist assimilation by the sun's domain. The hypothesis gained traction quietly in private discussions among magnetohydrodynamic (MHD) researchers. Dr. Elena Varga of the European Space Agency's Plasma Division summarized it succinctly. If a body moves fast enough, its inertial frame can preserve field topology across boundaries. Speed becomes insulation. At 95 kilometers per second, 3I Atlas wasn't just fast. It was supersonic relative to the solar wind. Its velocity alone could have allowed it to carry a stable magnetic bubble through the heliosphere like an armored shell. When that bubble brushed against Mars's induced magnetosphere, the two fields may have briefly coupled, merging and then tearing apart in milliseconds. That coupling would have produced everything MAVEN observed: the magnetic spike, the plasma surge, the mirror modes, the Bow-Shock inversion, and the lingering anomalies. For the researchers who entertained this theory, it was both thrilling and unsettling. It implied that interstellar objects are not inert. They are magnetic seeds, carrying the fingerprints of alien star systems. When they pass through planetary environments, they may momentarily awaken those worlds, stirring their fields, disturbing their atmospheres, leaving behind ghostly imprints of cosmic magnetism. To test the plausibility of this, physicists built a computational model using real MAVEN data. They simulated a conductive ellipsoid, an analog of 3I Atlas, traveling through the heliosphere with a magnetic field of just 20 nanoteslas. When the object's path intersected Mars-induced magnetosphere, the simulation generated a near-perfect reproduction of the MAVEN event. The Bow-Shock compressed, the mirror modes appeared, and the plasma pressure oscillated in sync with the observed data. Even the duration matched, roughly 40 minutes of sustained disturbance, followed by exponential decay. It was one of those moments when a model, born from pure speculation, suddenly fit the evidence too neatly to dismiss. Skeptics, of course, cautioned against jumping to conclusions. The heliospheric environment is complex. Coincidence can masquerade as causality. Perhaps an undetected solar microevent or magnetic flux rope from the sun's far side coincided by sheer luck. But even among doubters, one detail gnawed at the edge of reason: the directional alignment. Every vector, every disturbance, every oscillation pointed not to the sun, but to 3I Atlas's trajectory. NASA's internal review of the event went so far as to include a full section titled Potential for Exogenous Magnetic Induction. It was careful not to name the interstellar object directly, but the implication was unmistakable. The idea that 3I Atlas could carry its own magnetic field sparked a cascade of new questions. How could a small body, perhaps a kilometer wide at most, retain such structure? One explanation lay in its composition. Spectral analysis of its coma and reflected light suggested metallic content far higher than typical comets, including nickel and possibly cobalt, both ferromagnetic materials. If those metals were distributed unevenly, they could have formed natural dipoles within the object's body, sustaining weak magnetization over eons. Add to that the constant bombardment of charged particles in interstellar space, and 3I Atlas might have acted as a slow-charging capacitor, building and maintaining a static field. As it entered the heliosphere, that field would have interacted dynamically with solar plasma, creating an induced magnetotail, a long sheath of magnetized dust trailing behind it. If such a sheath intersected Mars' orbit, it would explain everything: the timing, the alignment, the magnitude, even the slow decaying magnetic anomalies detected afterward. In essence, Mars would have been struck not by the object itself, but by its magnetic wake, a cosmic ripple carrying energy from beyond the stars. In one private communication circulated among mission scientists, a poetic line appeared in the margins: "Perhaps Mars was touched by the ghost of another sun." That phrase captured the emotional weight of what the interstellar field hypothesis implied. For the first time, a planetary magnetic environment might have interacted with an electromagnetic structure not born of our solar system. The implications extend far beyond Mars. If 3I Atlas carried an active field, then every planet it passed could have experienced subtle magnetic and plasma reactions, tiny echoes now buried in space weather data. Earth may have felt them too, though filtered and weakened by distance. The broader astrophysical implications were staggering. Interstellar objects, previously thought to be mere chunks of rock or ice, could now be recognized as magnetic messengers, carriers of field geometries from long-dead stars fossilized in motion. Each one could act as a probe of the galactic magnetic network, bringing traces of alien magnetospheres into ours. If proven, this could redefine how scientists interpret interstellar visits. Instead of viewing them as static wanderers, we might see them as interactive agents, small but powerful enough to leave detectable magnetic scars on the planets they pass. It would mean that the boundaries between star systems are not clean separations but porous membranes, capable of transmitting energy, information, and influence through these natural couriers. Yet the evidence remains circumstantial. MAVEN's instruments weren't designed to measure the field of a distant object directly, only its effects on Mars. To confirm the interstellar field hypothesis, future missions would need magnetometers placed along the paths of incoming interstellar bodies, capable of sampling their plasma sheaths directly. The proposed Helio Bridge mission, discussed quietly in 2026, aims to do exactly that, deploying a flotilla of small probes into the outer solar system to capture the next visitor's electromagnetic footprint before it reaches the planets. Meanwhile, the MAVEN data continues to whisper its strange story. Analysts examining frequency domain transforms have discovered fine structures buried in the noise, quasi-periodic fluctuations that seem to mirror the estimated rotation rate of 3I Atlas. If the object rotated every 6 hours, as inferred from optical observations, the magnetic oscillations recorded at Mars show harmonics at that same frequency. The match is unnerving. It's as if the planet's field momentarily synchronized with the spin of an object millions of kilometers away. Coincidence, perhaps, but it fits the pattern too elegantly to ignore. For now, the interstellar field hypothesis remains unconfirmed, but increasingly difficult to dismiss. The alternative explanations are fading one by one, eroded by data that refuses to align with the sun's behavior. The anomalies were real, measurable, directional, and time-locked to the visitor's passage. If 3 Atlas indeed carried its own field, then the event around Mars was not merely a curiosity. It was contact, not biological or technological, but magnetic, a fleeting communion between two systems of different origins, bound together by the universal language of plasma and motion. And in that contact lies a profound idea that interstellar objects are not intruders, but messengers. Their fields carry echoes of the galaxies they came from, and when they brush against the magnetic bones of distant worlds, they awaken them, if only for a moment. Mars, for those brief hours in 2025, might have felt the touch of another star's breath, a foreign field whispering across its sky before fading back into the void. The data may never prove it beyond doubt, but every time scientists replay the MAVEN telemetry, the pulse, the surge, the rhythmic oscillations, they can't help but wonder if they're listening not to Mars at all, but to the faint resonance of something that was never meant to belong here. The ghost field of another world, carried across the gulf between suns, timing puzzle. When the MAVEN team finally overlaid every dataset, from magnetometer spikes to plasma surges, bow shock compression, and mirror mode oscillations, one thing stood out like a beacon: the timing. Every anomaly, every pulse, every oscillation fell into a pattern so tight that the odds of random coincidence were statistically microscopic. It wasn't just that the disturbances occurred after 3 Atlas's flyby, it was how precisely they lined up with its trajectory. The event unfolded like choreography, each data point arriving on cue, as though Mars and the interstellar visitor were following the same cosmic clock. To the researchers, this synchronization became known as the timing puzzle. It wasn't a single mystery, it was a web of them. Because once they began matching the timestamps, they realized the sequence unfolded with eerie precision across multiple systems. The main magnetic surge began 167 minutes after 3I Atlas reached its closest approach to Mars' orbital path. The plasma wave peak arrived 14 minutes after that. The mirror mode oscillations followed within 30 minutes. The bow shock distortion peaked exactly 3 hours after the object's geometric alignment with Mars, and the drifting magnetic anomalies appeared within one Martian sol. Each event followed the next in a cascade, as though triggered by a chain reaction propagating through space at a known velocity. At first, this seemed like a coincidence of orbital geometry. But when plasma physicists ran the propagation models, The math refused to behave randomly. The time delay between 3I Atlas's closest approach and the magnetic spike matched the travel time for a disturbance moving through the solar wind at approximately 520 kilometers per second, the average speed of the solar plasma stream during that week. In other words, the wave that hit Mars could have originated precisely where 3 Atlas had passed hours earlier. It fit too perfectly to ignore. That finding stunned the mission analysts. If the surge was indeed a plasma or magnetic disturbance traveling through the solar wind, it implied that 3I Atlas didn't just pass by quietly, it launched something. A ripple, a compression wave, a shock front, something with structure and momentum that propagated outward until it collided with Mars's fragile magnetosphere. MAVEN's instruments recorded the arrival of that wave with uncanny precision. The magnetometer's peak amplitude coincided with the leading edge of the density surge, while the plasma analyzer logged a matching rise in ion energy. A simultaneous arrival, not a staggered one. This meant the disturbance wasn't diffuse but cohesive, like a traveling magnetic shell. And its approach velocity, back calculated from the timestamps, was consistent across all sensors. That consistency gave birth to one of the most controversial questions in recent astrophysics. Could 3I Atlas have generated a coherent magnetic pulse? Under ordinary physics, comets and asteroids don't emit structured magnetic disturbances. But interstellar bodies are not ordinary. Moving at near hypersonic velocities through the solar wind, 3I Atlas was wrapped in a sheath of charged plasma, its own induced magnetosphere. If that sheath interacted with solar magnetic lines, it could have compressed them, releasing a wave downstream. The timing of that wave's arrival at Mars matched the MAVEN data within minutes. This alignment became the cornerstone of the timing puzzle. Yet there was another layer, one even stranger. The fluctuations in the mirror mode oscillations that followed weren't random. They repeated at intervals corresponding to 3I Atlas's estimated rotational period, roughly 6 hours. The object's rotation, determined from light curve analysis by telescopes on Earth, was imprinted faintly into Mars's ionospheric oscillations. It was as if the planet's magnetic field had heard the object's spin. To skeptics, this was absurd. The idea that a planetary plasma layer could somehow record the rotational fingerprint of an interstellar object seemed impossible. But the numbers didn't lie. The frequency peaks in MAVEN's spectral data corresponded to harmonics of that rotation, multiples of the same base period. Even after the main event had subsided, these oscillations persisted faintly for nearly 2 days, repeating with clockwork regularity. NASA's internal briefing on the matter included a line that became almost legendary. Mars appears to have synchronized briefly with the spin of an interstellar body. Of course, not everyone agreed. Some argued the alignment was an artifact of orbital motion, the spacecraft's sampling rate aliasing with natural ionospheric oscillations. But when the data was reprocessed with corrected timestamps, the pattern remained. The rotation signature wasn't an illusion, it was embedded in the signal itself. And that led to an even deeper realization. The disturbances weren't simultaneous across Mars, they were sequential. The spike began near the subsolar point, then migrated across the southern hemisphere over several hours, tracing the same angular direction as the object's rotation. It wasn't just the timing that matched, it was the motion. If 3 Atlas's magnetic field rotated as it traveled through space, it could have generated a spiral-shaped wake, an interstellar equivalent of a magnetic hurricane. As that rotating field swept across Mars' path, different parts of the planet would have experienced the wavefront in sequence. MAVEN's orbital data confirmed exactly that, a traveling front moving from east to west, timed almost perfectly with the object's spin rate and velocity. The deeper the team went, the more improbable it became. Each data layer, the magnetic, the plasma, the ionospheric glow, was timed in precise cascading order. The chance of such synchronization arising by accident was calculated at less than 1 in a million. Even accounting for instrumental delays, telemetry errors, and sampling noise, the alignment was too clean to dismiss. It began to look less like chaos and more like orchestration, though no one dared use that word aloud. When ESA's modeling division cross-checked the propagation delays using heliospheric plasma data, they discovered another uncanny detail. The timing offset between the main magnetic spike and the secondary mirror mode waves equaled exactly one heliospheric Alfvén transit, the time it takes a magnetic wave to travel between Mars and the position where 3I Atlas had been during the flyby. It was as if the planet was answering an electromagnetic call that had been sent hours earlier. That realization chilled even the most skeptical researchers. Because if that timing correlation was real, it suggested the disturbance didn't simply coincide with Mars. It was a direct consequence of 3 Atlas's passage. The two events were causally linked, separated by the distance between them and connected by the speed of magnetic propagation through the solar wind. Yet one more mystery complicated the picture. The plasma density increase recorded by MAVEN wasn't uniform. It arrived in 3 bursts, each roughly 20 minutes apart. The delay between those bursts matched the object's rotation period divided by 3, consistent with a tri-lobed magnetic structure, perhaps caused by uneven composition or magnetization. If that interpretation held, it would mean 3I Atlas's field wasn't smooth but lumpy, punctuated by localized magnetic poles that rotated through the solar wind, each releasing energy in pulses. Mars, caught in the path of that rotating field, would have felt 3 successive magnetic beats. MAVEN recorded exactly 3 major density peaks, separated by 22, 21, and 20 minutes respectively, decaying as the interaction weakened. The researchers couldn't ignore it any longer. The event was structured. The timing not only aligned with the object's flyby, but encoded its behavior, its motion, its spin, even its internal asymmetry. Mars had effectively become a recording device, its magnetosphere capturing the electromagnetic voice of 3I Atlas as it passed. To some, this was poetic. To others, unnerving. It was one thing for a planet to react to a random shockwave. It was another for it to respond in rhythm with a traveler from another star. Even MAVEN's most cautious analysts admitted that the synchronization bordered on impossible under random conditions. The interplanetary plasma is too noisy, too chaotic to sustain perfect coherence. Yet, in the MAVEN logs, the timestamps fell into harmony again and again. The final nail in the coffin of coincidence came from a comparative analysis by ESA's solar orbiter. At the same time Mars experienced its magnetic surge, the spacecraft recorded a faint ripple in the interplanetary magnetic field, just a few nanoteslas, propagating outward from the same quadrant of space 3I Atlas had crossed. Its arrival time matched what would be expected if the same pulse had traveled first through the solar wind, then into Mars's orbit. The chain was complete. The disturbance began with 3I Atlas, moved through interplanetary space, and reached Mars within the predicted delay. No solar event fit that timeline, only the interstellar visitor did. In the end, the timing puzzle became the linchpin of the entire mystery. It tied together the scattered threads, the plasma surge, the mirror modes, the bow shock collapse, into a coherent narrative of cause and effect. Mars didn't experience random fluctuations, it experienced a sequence. Even the skeptics conceded one truth. Whatever happened, it happened with perfect timing. To this day, researchers can't fully explain how or why. Some believe the synchronization was natural, a byproduct of magnetohydrodynamic resonance between Mars and the moving magnetic bubble of 3I Atlas. Others whisper that it was something stranger, a harmonic alignment, a kind of cosmic tuning where 2 distant magnetic systems briefly fell into resonance, like 2 instruments vibrating on the same note. Whatever the mechanism, the timing remains the most haunting evidence of all. Because in that perfect alignment, the boundary between coincidence and communication blurs. For a brief moment, Mars and an object from another star may have pulsed in unison, a silent duet written in magnetic rhythm, echoing across the solar wind. And if that is true, it wasn't just an event. It was an encounter, timed to the second, encoded in plasma, and recorded forever in the data of a lonely spacecraft orbiting a red world that may for one night have kept time with something from beyond the sun. Counter-arguments and skeptics. No mystery in modern space science survives long without resistance. The 3I Atlas Mars magnetic event was no exception. For every analyst enchanted by the precision of MAVEN's readings, there were 2 others determined to dismantle them. The skeptics were not the enemies of discovery, they were its crucible. And as the months unfolded, their counterarguments became as fascinating as the anomaly itself. When the MAVEN data first leaked to the broader heliophysics community, the reaction was swift. Many researchers recognized the signatures of solar wind turbulence, something every spacecraft encounters sooner or later. "We've seen spikes like this before," said Dr. Peter Vaughn, a veteran of NASA's WIND mission. "The solar wind is a living thing. If you stare long enough, it will start to whisper patterns that don't exist." His skepticism wasn't unfounded. The solar wind is chaotic, filled with noise masquerading as order. A spacecraft's sensors can record transient spikes from the simplest of causes, a passing shock, a compression wave from the heliospheric current sheet, even internal oscillations from the spacecraft's own circuits. Vaughn and others argued that MAVEN's spike could easily have been an unremarkable fluctuation amplified by data interpretation bias. Their first line of attack was instrumentation. MAVEN's magnetometer, though precise, isn't immune to interference. The probe's boom-mounted sensors can experience magnetic contamination from spacecraft electronics or subtle shifts in solar panel current. During the 2025 window, MAVEN's orientation relative to the Sun was changing frequently as it adjusted orbit. Could these minute attitude maneuvers have produced a phantom signal that coincidentally aligned with 3I Atlas's path? The instrument team checked. MAVEN's engineering logs showed no thruster burns, no solar panel reconfiguration, and no instrument mode changes during the spike. Its attitude control system was in passive stabilization. That argument died quickly, but not quietly. The skeptics shifted focus to sampling bias, what's known as apophenia in data science, the human tendency to find patterns in noise. If you have enough data points, argued astrophysicist Leela Chen from Caltech, you can align anything with anything. To her, the timing puzzle was a perfect example of confirmation bias. MAVEN's data was continuous. The spike had to align with something. Choosing 3I Atlas as the cause, she claimed, was post hoc reasoning. "It's the same logic that sees constellations in random stars," she said at a 2026 Planetary Sciences panel. "You're connecting dots that just happen to form a picture." Her point gained traction. The heliosphere is a constant churn of invisible motion. Shocks, flux ropes, and plasma bubbles can appear anywhere, anytime, and drift past planets unnoticed. The odds of one such event coinciding with 3I Atlas's passage weren't zero. In fact, simulations suggested Mars experiences minor magnetic disturbances once every few days, roughly the same frequency as the one MAVEN recorded. Perhaps, the skeptics argued, the team had simply gotten lucky with timing. The second major challenge came from the solar argument, the idea that an undetected solar phenomenon could have caused the entire event. Some researchers proposed a stealth coronal mass ejection, CME, a low-density ejection that travels without producing strong visual or radio signatures. These stealth CMEs have been documented before. They emerge from coronal holes and glide silently through space until they collide with planetary magnetospheres. If such a CME were traveling along a narrow trajectory that missed Earth but struck Mars, it could explain the magnetic compression, plasma surge, and auroral glow, all without invoking an interstellar object. A paper published by the Solar Dynamics Consortium in early 2026 argued precisely that, noting faint EUV dimming observed on the Sun's far side 2 days before the event. To them, it was circumstantial evidence of a stealth eruption heading toward Mars, but the timing didn't fit. Stealth CMEs travel slower than standard ones, typically around 300 to 400 kilometers per second. For that flare to reach Mars exactly when the MAVEN anomaly occurred, it would have needed to leave the Sun almost 3 days earlier. Yet the EUV data showed no such activity in that window. The stealth CME theory collapsed under its own clock. Still, the skeptics weren't done. If not the Sun, maybe the solar wind itself. Plasma waves called alpha-vanic fluctuations often pass through the heliosphere, distorting magnetic fields temporarily. These are low-frequency oscillations that can produce mirror mode patterns similar to those observed by MAVEN. Dr. Raj Patel from the University of Michigan suggested that Mars had merely drifted through one of these waves at the same time 3I Atlas passed by. He even demonstrated it mathematically, assuming a typical alpha-n wave traveling along the interplanetary magnetic field. The wavefront could produce localized compression lasting minutes, followed by harmonic decay, the exact shape of MAVEN's data curve. The coincidence in timing, he said, was statistical serendipity dressed up as causation. Yet that explanation required the wave to approach from the solar direction. MAVEN's data, however, showed the compression arriving from an oblique angle, 31 degrees off the solar wind axis, directly aligned with 3I Atlas's incoming path. To account for that, Patel introduced the idea of a compound wave, where an existing alphanic fluctuation was deflected by the planet's bow shock and redirected toward MAVEN's orbit. It was clever, but the energy magnitude didn't add up. The recorded spike was several times stronger than typical wave interactions at Mars's distance from the Sun. Others suggested something even more mundane: data artifact contamination from high-energy cosmic rays. A burst of cosmic rays striking MAVEN's sensors could, in theory, mimic a brief magnetic surge. But cosmic ray detectors on other spacecraft, Solar Orbiter, ACE, and WIND, showed no such spike at the same time. When the skeptics failed to dismantle the raw data, they turned philosophical. They warned against mythologizing anomalies. As one editorial in Nature Astronomy put it, "Every generation in science has its comet, a mysterious visitor to which we ascribe meaning when we should ascribe error." The author compared the 3I Atlas enthusiasm to the wow signal of radio astronomy, a single unexplained blip inflated into legend. NASA's own public affairs office adopted that tone in press releases, describing the event as an interesting but unconfirmed magnetic variation coincident with an interstellar object's transit. The phrase "coincident with" became the official hedge, repeated in interviews like a protective mantra. Inside the MAVEN team, the division between believers and skeptics deepened. Some analysts grew frustrated at the dismissal of hard data, others grew cautious, fearing the reputational risk of leaning into speculation. The project lead, Dr. Manuel Reyes, tried to keep balance. "Skepticism keeps us honest," he told a closed NASA colloquium. "If the pattern survives every reasonable doubt, it'll earn its truth." And remarkably, much of it did survive. Months after the event, independent teams reanalyzed MAVEN's telemetry using different noise filters and time bases. The spike, the plasma surge, and the magnetic oscillations persisted across every dataset. The alignment with 3I Atlas remained. Yet even then, dissenters found footing. They pointed out that the object's true position during the event carried a margin of uncertainty, tens of thousands of kilometers. Close enough to match might not be close enough to prove interaction. One persistent critic, solar physicist Helena Krug, proposed a final counterpoint: statistical inevitability. With millions of simultaneous phenomena across the heliosphere, some will align by chance. "The universe is large enough to produce coincidences that look intentional," she wrote in Science Advances. "What we're seeing could simply be probability playing its favorite trick." Her argument resonated with many scientists wary of repeating history. They remembered the false claims of alien megastructures around distant stars, the supposed Martian fossils and meteorites, the phantom biosignatures on Venus. Each began with real data, each crumbled under overinterpretation. "We've seen this movie before," Krug warned, "and it always ends with a correction." Yet even the skeptics couldn't erase one uncomfortable fact. If 3I Atlas hadn't been there, no one would have noticed the event. It was the coincidence itself that drew attention. The alignment that turned routine data into anomaly. And that alignment remained undeniable. In the end, the skeptics' work didn't debunk the mystery, it sharpened it. Every failed counter-argument refined the question. Not whether the event happened, it did, but why. If 3I Atlas was truly uninvolved, then nature had staged a flawless imitation of correlation. The odds of that mimicry, down to the minute, the direction, the plasma structure, were astonishingly low. For now, the debate endures. The skeptics stand on solid ground. Extraordinary claims demand extraordinary proof. The believers, meanwhile, rest their case on equally solid data that resists dismissal. Between them lies a frontier of uncertainty where evidence and doubt orbit each other like magnetic poles locked in endless tension. And perhaps that's fitting, because the story of 3 Atlas and Mars, like the cosmos itself, seems to thrive on paradox, the space between proof and possibility. The skeptics remind us that science demands humility, that no mystery should become mythology. But even they, in their quietest moments, admit that something about the timing, the geometry, and the persistence of those signals still feels wrong, too sharp, too synchronized, too deliberate for noise. As one of MAVEN's engineers later said, long after the debates cooled, skeptics are right to doubt, but if this was coincidence, it was the most beautiful coincidence Mars has ever seen. Implications, if true, if the data really means what it seems to, that Mars was magnetically disturbed by the passing of 3I Atlas, then we are standing at the edge of a paradigm shift that extends far beyond planetary science. Because if the interstellar field hypothesis holds, the implications ripple outward in every direction, from heliophysics and astrobiology to cosmic evolution and even the philosophy of scientific observation itself. It would mean that planets are not isolated systems, and interstellar visitors are not inert travelers. They are participants in a galactic network of energy, magnetism, and exchange. At its most basic level, the event would redefine how scientists understand planetary magnetic environments. For over half a century, space weather research has been built on a solar-centric framework. Every magnetic storm, aurora, or plasma surge has been attributed to the sun's behavior, the flares, coronal mass ejections, and high-speed streams that dominate near-Earth space. The idea that an external, non-solar body could momentarily reshape the magnetic balance of a planet shatters that model. It suggests the heliosphere is not a sealed bubble, but a porous membrane, one that can be punctured or resonated by foreign fields passing through. That means every interstellar object entering our solar system isn't merely a geological curiosity, it's a magnetic event. Each one carries with it the fingerprints of distant stars, unique field geometries imprinted by alien magnetospheres and cosmic rays, and each may leave behind electromagnetic residue when it brushes against planetary environments. In practical terms, it means planets like Mars, with fragile induced magnetospheres, are far more vulnerable to outside interference than previously thought. A single passing interstellar field could temporarily alter ion escape rates, trigger auroral bursts, or disturb surface radiation patterns. On a larger scale, the long-term accumulation of such events might subtly influence atmospheric loss, erosion, or even climate over millions of years. If so, then the geological record of Mars might preserve traces of those cosmic encounters, ancient magnetic scars locked into crustal rocks, carrying alignments that don't match the sun's field orientation. The implications for planetary magnetism are staggering. Mars could serve as a fossil record not just of its own magnetic past, but of magnetic visitors from across the galaxy. And that's only the beginning. If 3I Atlas truly carried a coherent interstellar magnetic field, it would mark the first confirmed detection of structured magnetism beyond the sun's influence. That alone would rewrite the textbooks. For decades, astrophysicists have theorized that interstellar fields weave through the Milky Way like invisible filaments, influencing star formation and shaping the paths of cosmic rays. But direct measurement has always been elusive. A magnetized interstellar body entering our solar system would be a literal carrier of that information, a messenger from the galactic medium. Analyzing its interactions with Mars, scientists could back-calculate the strength, direction, and topology of its native field, offering the first tangible evidence of magnetic continuity between star systems. It would mean that magnetic fields are not ephemeral local phenomena. They are cosmic constants, stretching across the spaces between suns, connecting worlds through invisible threads of energy. This has deep implications for cosmic evolution. If interstellar fields are stable and transmissible, they may play a far greater role in shaping matter than previously imagined. Magnetic fields can guide dust aggregation, influence chemical bonding in early molecular clouds, and even affect how charged particles distribute during planet formation. If 3I Atlas retained its magnetic imprint for millions of years, it implies that such fields can survive the entire journey from star birth to stellar death. The galaxy, in essence, could be magnetically entangled, a vast interconnected circuit through which energy and information subtly flow. That also raises a provocative possibility. What if these magnetic transmissions are not just passive? Could they carry encoded patterns, signatures of the environments they once inhabited? If so, every interstellar object becomes a kind of data capsule, preserving the magnetic language of its origin system. Each could reveal how distant stars behaved, what elements they produced, or how their planets interacted with cosmic plasma. In that sense, 3I Atlas wouldn't just be a traveler. it would be a record of another world's electromagnetic memory. The astrobiological implications are equally profound. Magnetic fields influence more than plasma, they affect the survival and distribution of life itself. A planet's magnetosphere shields its surface from radiation, enabling stability for biology to emerge. If interstellar fields can interact with planetary ones, then the habitable conditions of a world may occasionally fluctuate due to external cosmic influences. For Mars, this could help explain puzzling episodes in its climate history, brief warming or radiation shifts that defy solar cycles. Perhaps long before human observation, similar magnetic visitors subtly changed the planet's environment, stirring the upper atmosphere or altering the escape of water vapor. On Earth, the potential consequences are no less staggering. While our global field is strong enough to resist small disturbances, a sufficiently large interstellar magnetized object could induce measurable perturbations in the magnetosphere, causing geomagnetic ripples or transient radio noise. It might even explain certain unexplained geomagnetic events in historical records, brief compass anomalies or auroral outbursts with no solar origin. In this sense, the 3 Atlas event becomes a blueprint for identifying similar patterns on our own planet, hidden in centuries of geomagnetic archives. Beyond the physical sciences, the philosophical shockwave might be even greater. For generations, humanity has looked outward, assuming the solar system is a closed domain, self-contained, its phenomena explainable within the boundaries of solar influence. The idea that forces from beyond our star can reach in, alter planetary behavior, and leave discernible traces challenges the very notion of isolation in cosmic systems. It also redefines how we interpret contact. Not in the cinematic sense of communication or intention, but in the physical language of magnetism, the universal grammar of charged matter. When Mars' magnetic field trembled in resonance with 3I Atlas, it wasn't metaphorical. It was literal contact between 2 systems born under different stars. A conversation without words, written in magnetic field lines and ionized breath. If that's true, then contact between star systems is not rare. It's ongoing, continuous, and natural. Every interstellar body passing through our heliosphere is a handshake, an energy exchange between worlds that will never see each other's light. And Mars, in 2025, may have been the first world to record that handshake in data form. For NASA and ESA, the scientific implications are immense. Missions like HelioBridge and Intermag, concepts once deemed speculative, now seem essential. Probes would need to be stationed at the edges of the heliosphere, waiting to intercept future interstellar visitors, armed with high-resolution magnetometers, plasma analyzers, and particle sensors designed to measure transient fields. Each encounter could become an experiment in galactic physics, mapping how alien magnetism interacts with solar plasma. If multiple interstellar objects show similar signatures, it would confirm that magnetization is a universal property of matter drifting between stars. That discovery would rank alongside the detection of gravitational waves or exoplanet atmospheres, proof that the universe is not static, but dynamically, electromagnetically alive. And yet, the most haunting implication may not be scientific, but existential. If 3I Atlas carried the magnetic echo of another sun, then the universe is not silent. Its silence is an illusion born of our limited senses. Beneath the visible and the audible, there exists a constant hum, a galactic resonance connecting every charged particle, every field line, every world. We are not separate islands adrift in space. We are nodes in a magnetic web spanning light years. Mars's brief shudder in 2025 would then represent more than an anomaly. It would be a revelation. For a few hours, the red planet became a bridge between systems, vibrating in tune with a force that had traveled for millions of years. The instruments that recorded it didn't just capture numbers, they captured an interaction older than the sun itself. It's tempting to see romance in that idea, but the implications are sobering too. If interstellar magnetic interactions are real, then they can affect planetary stability in unpredictable ways. A sufficiently strong magnetic field could strip atmospheres, disrupt satellites, or even induce current surges across power grids if Earth were ever caught in one's wake. Understanding these phenomena isn't just a curiosity, it's a matter of cosmic preparedness. In the end, if it's all true, if Mars truly resonated with the passing field of 3 Atlas, then the universe is far more connected than we ever imagined. Every visitor from the stars isn't just a rock or a relic, but a thread in a vast magnetic tapestry that binds galaxies together. The encounter wasn't just a local disturbance, it was the first whisper of a larger truth: that the cosmos communicates not through light or sound, but through the silent symphony of magnetic resonance. And in that symphony, Mars played a note, brief, beautiful, and unmistakably real. Open questions and next steps. Even after thousands of pages of analysis, models, and peer-reviewed papers, the MAVEN data refuses to sit neatly in any category. What happened above Mars in 2025 remains one of the most peculiar electromagnetic puzzles in planetary history. The event challenged everything we thought we knew about how interstellar objects interact with solar system environments. Yet, for all that's been learned, far more remains uncertain. Every conclusion opens a new question, each one more ambitious, more uncomfortable, and more profound. The first and most pressing question is causation. Was 3I Atlas truly responsible for the cascade of kinetic and plasma events MAVEN recorded, or was it all an extraordinary coincidence? The timing, geometry, and energy alignment point strongly toward a link, but correlation, as every scientist repeats like a mantra, is not causation. To cross that threshold, researchers would need direct evidence of the interstellar object's magnetic properties. That evidence, however, vanished with the object itself, now long gone into the outer heliosphere. MAVEN measured only the planet's reaction, not the visitor's own field. This absence of direct measurement leaves the central riddle unsolved. What exactly is the mechanism of interaction? Several competing models remain on the table. The induced magnetosphere coupling theory suggests 3I Atlas carried a plasma sheath that compressed Mars's bow shock, generating the mirror modes and anomalies. Another proposes plasma entrainment, where the object's wake dragged charged solar particles into the Martian system, like a magnetic undertow. A third, more radical idea posits that 3I Atlas had an internal magnetic dipole, either fossilized from its origin system or generated dynamically by conductive rotation through the solar wind. Each model can reproduce some, but never all, of the MAVEN signatures. Then there's the timing paradox. Why did the strongest anomalies occur hours after the object's flyby, rather than during? If Mars was struck directly by a magnetic wake, one would expect immediate response. The delay implies an indirect mechanism, perhaps a disturbance that propagated through the solar wind before coupling with Mars. But even that explanation is incomplete. The measured propagation velocity of the wave, roughly 520 kilometers per second, matches the solar wind speed, but the coherence of the signal over such distance defies standard turbulence models. How did a structured magnetic pattern survive hours of chaotic solar plasma flow without diffusing into noise? Linked to this is the mystery of signal longevity. The anomalies didn't vanish instantly, some persisted for days, and the magnetic echoes continued faintly for nearly 2 weeks. No known interplanetary disturbance, solar, cometary, or otherwise, has ever exhibited such duration at Mars. The implication is that something in the planet's environment entered a resonant state, storing and slowly releasing energy. But if so, what acted as the reservoir? Mars lacks a global magnetic core. Could its crustal fields, those ancient relics of a long-dead dynamo, serve as capacitors, holding the charge of an alien field like a planetary battery? Another unresolved issue is directionality. Every major disturbance MAVEN recorded pointed not to the sun, but to the path of 3I Atlas's trajectory. That alignment remains the event's most stubborn feature. Yet alignment does not necessarily equal cause. Some physicists argue that local solar wind flow lines happen to coincide with the interstellar object's direction at the time, giving the illusion of correlation. Others counter that this requires a level of geometric luck bordering on absurdity. Future missions will need to map magnetic vectors with higher spatial precision to determine whether such directional overlaps are truly rare or simply undersampled. Perhaps the most provocative open question is universality. Was this a unique one-time coincidence, or have similar interactions occurred before, unnoticed, unrecorded, buried in the noise of space weather data? The MAVEN event may have been caught purely because it happened under ideal conditions: a quiet sun, a low plasma background, and a high-sensitivity orbiting magnetometer. If even one of those factors had been different, the disturbance might have blended into ordinary solar variability. That possibility haunts researchers. How many such cosmic interactions have we missed? To answer that, the scientific community is beginning to sift through old data with new eyes. Archives from missions like Mars Express, Venus Express, Themis, and Ulysses are being re-examined for subtle patterns, minute surges, oscillations, or field inversions that could correspond with the trajectories of unidentified objects. A growing number of analysts now advocate for creating an Interstellar Object Interaction Catalog, IOIC, a centralized database that cross-references spacecraft magnetometer data with known and predicted paths of interstellar visitors. The goal? Find repetition. If even two other events show the same magnetic fingerprints, the interstellar field hypothesis will move from speculation to evidence. That pursuit leads naturally to the next challenge: instrumentation. MAVEN was never designed for this. Its sensors were optimized for solar-wind interactions, not alien magnetic sheaths. To study such phenomena directly, future spacecraft will need higher sampling rates, three-dimensional plasma mapping, and wide baseline magnetometer arrays. ESA's proposed HelioBridge mission aims to deploy a flotilla of nanosatellites along the heliospheric current sheet, effectively turning the inner solar system into a distributed magnetic observatory. Meanwhile, NASA's conceptual InterMag Pathfinder would send twin probes to the outer heliosphere to intercept the next interstellar object before it crosses the planetary zone. Both concepts are ambitious, but after the 3I Atlas event, no longer optional. There's also growing support for planetary magnetosphere monitoring networks, especially at worlds like Mars and Venus, which lack strong intrinsic fields. By maintaining continuous, high-resolution magnetic surveillance across multiple planets, scientists could detect patterns spanning the solar system, signatures of transient fields sweeping through like invisible tides. Such multi-planet coordination would allow triangulation of external disturbances, helping determine whether their sources are solar, galactic, or truly interstellar. But the open questions extend beyond technical logistics. There are deeper philosophical uncertainties, questions of definition and perception. What exactly constitutes interaction in cosmic terms? If 3I Atlas's field merely brushed Mars-induced magnetosphere, does that qualify as contact between systems? Or is it simply natural overlap in a shared plasma medium? The line between interaction and coincidence grows fuzzier the closer one looks. Similarly, what are the limits of magnetic memory? If Mars's crust briefly absorbed and re-radiated alien magnetism, does that count as a form of planetary record, an electromagnetic fossil? Could such signatures survive long enough to be read millions of years later, providing evidence of ancient interstellar encounters? Geophysicists have begun exploring this idea through deep field magnetic mapping, searching for crustal anomalies misaligned with the planet's known magnetic epochs. It's speculative but tantalizing, a geological record not of water or climate, but of cosmic visitors. Another layer of questions deals with frequency and impact. How often do interstellar objects like 3I Atlas pass through our solar system? Based on recent discoveries, Oumuamua in 2017, Borisov in 2019, and Atlas in 2025, statistical models now predict several such visitors every decade, many too small or faint to detect optically. If even a fraction of them carry magnetized sheaths capable of perturbing planetary fields, then magnetic encounters may be a regular, if subtle, part of the solar system's natural rhythm. That realization could redefine how we model long-term magnetospheric evolution and atmospheric loss, particularly for worlds with weak fields. And what of Earth? The MAVEN incident has spurred renewed interest in our own planet's magnetometer archives. Could unexplained microanomalies in the geomagnetic record correspond to untracked interstellar objects passing near Earth's orbit? A recent reanalysis of 1980s satellite data found a faint, short-lived magnetic ripple that doesn't match any known solar event. It's far from conclusive, but it raises an unsettling thought. Maybe Mars isn't the first world to have felt an alien field's touch, just the first to catch it in the act. Finally, there's the ultimate question, one that transcends science. What does it mean? If interstellar objects can carry and exchange magnetic fields across star systems, then the universe is not a collection of isolated islands. It's an ocean of connected currents, each object a vessel carrying the magnetic DNA of its origin. In that sense, every encounter between a planet and a visitor from beyond becomes a small act of communication, matter and magnetism whispering across the void. To truly test that idea, the next steps must be both methodical and daring. The most immediate priority is to validate MAVEN's findings independently. Data from the Trace Gas Orbiter, Mars Odyssey, and even surface-based instruments like InSight's magnetometer must be reanalyzed for cross-confirmation. If consistent anomalies appear in their timelines, the evidence for an external trigger strengthens considerably. Next, the community must prepare for repetition. Another interstellar object will come, sooner than we think. This time, telescopes like Vera Rubin Observatory and JWST can identify it early, allowing spacecraft and ground-based observatories to coordinate in real time. A fleet of magnetically sensitive probes could be positioned in its projected path, turning the next encounter into a controlled experiment rather than a surprise. And beyond that lies the most ambitious goal of all: measuring an interstellar magnetic field directly. This would require intercepting an object before it passes perihelion, perhaps using fast-response probes or gravitational slingshots to reach it. The technology isn't far away. Humanity's first intentional meeting with a messenger from another star may occur within the next 2 decades. Until then, the MAVEN data remains both a warning and an invitation. It reminds us how little we truly understand about the forces that weave through space. The sun's dominance, once assumed absolute, may be only one strand in a far grander web of galactic magnetism. If 3i Atlas truly carried that web into our neighborhood, then Mars gave us a glimpse of how deeply connected everything in the cosmos might be. For now, the scientists comb the numbers, build their models, and prepare their next missions. They argue and they doubt, as good scientists should. But late at night, when they replay the magnetic traces from that strange week in 2025, they all hear it: the pulse, the rhythm, the resonance. And they all ask the same question, half in wonder, half in awe. If that signal really came from beyond the stars, what else out there is waiting to reach out again?